a bunch of slides. I'll do 40 slides in 10 minutes. But the point is, get everyone in the room up to speed as fast, so everyone in the room knows what they're talking about. Once you have people understanding the problem, then you can have a live discussion. It's very important that the microconference runner watch for tangents, bike shedding, things that will waste time. You could say, we could discuss that later. So when you really try to keep involved with the conversation that's going on, if someone starts talking about a little detail, everyone knows that when that happens, you've been in a meeting and then you find out that we just spent the whole meeting talking about if it should be, input A or input B. You're like, who cares? It's not helping the problem. Look at what the objective of the microconference topic is and stick to it. And because you say time is of essence, it's 20 minutes. It's very short. Once the 20 minutes are up, you basically have to stop them and say, sorry, we have to stop right now. The idea also is during those 20 minutes, try to make it so that it'd be easy to do the hallway track, emails, mailing lists. Say, continue this to the mailing list. Which brings up another key point, notes. Take notes while you're doing it. You're going to be doing 20 minutes and you're like, oh yeah, I'll remember that. And then the next 20 minutes, you're focused on something else. The next 20 minutes, you're focused on something else and you're going to forget. If you look in there, there's a shared notes. Try to keep up with that. If there's something broken with that, open up in your editor or anything and cut and paste it. Be careful when you exit out, especially if you're moderators, up on the top, and let me steal it. Wait, can I steal the screen again or are you uploading? It's not going? Wait, so you did it through this?
Yes, but I have to.
It's a good time. Which one?
It's the first one. I don't know why.
And then you hit this and then you sit up.
I said you loaded. Something went wrong.
Okay, actually, maybe I should have you do is I wish James Bottomley or Mike Rappaport was here. And Tim Bird. They're the kind of our technical people. So if you know Mike Rappaport, Tim Bird, or James Bottomley, they're kind of supposed to be on the tech team. So try to find them, and if you're having issues with technical issues there's everything.
Is there like a matrix channel?
Yes, there's a matrix channel that you can log in. James Bottomley loves Matrix, so everything is through Matrix with him, and I actually have trouble logging into it. So you got it? Oh, see? There. Awesome. And then, yes. How to upload the slides? Are you, okay, no, but are you a square or a circle? No, if you look onto the left side of your account. Yes. So are you? So yeah, the most important thing, to log in, you have to go to log into meet.lpc.events. That's what this is, meet.lpc.events. That's where this will be. So please, yeah, that's what you should get. And right now you have the video. Trying to think this, got everything else. So yeah, the idea again is to make sure everyone goes from 10, after the 20-minute session is done, go to the next one and move on. It's going to be, if you haven't done this before, it's kind of intense. I love the conference, doing this. That's also, like I said, try to make sure that people do explain things, ask questions. Don't assume that everyone in the room knows it. Remember, plumbers means there's experts in other fields might be sitting in your microconference. So acronyms and everything else, please try to, explain things. The one reason, one year we tried to get rid of slides because we always said slides were really a bad thing. So we try to limit slides. And I hate to say this, I'm going to use the scheduling RT conference as the reason why I found out that was a bad idea. You got, okay, no slides. And basically, I remember you're talking about one thing, 3 people in the entire room, there's over 100 people in the room, 3 people had an idea what was going on. And I was like, this conversation could have happened in a pub. It didn't need to be at Plumbers. And that's when I realized that the no slide rule or limited slides was a mistake. I like slides because the idea of slides should be educating. The slides should focus, here is my problem. Here is what I want to discuss about. Everything should be focused on the discussion so you get input from the people that you're talking with. Okay, any questions? Because I think we're pretty much out of time now, or almost. This is just, like I said, short thing. If you have any questions, feel free. If there's anything else you want, feel free to ask me. Was that? I know. My old boss is over there. So, okay, well, that's basically it. Upload your slides if you have trouble uploading your slides, and make sure when you log in, you're okay. Make sure everyone here, when you log in, is a square, not a circle. So if you don't know what I mean, look over on the left side of that. You'll see squares and circles. Squares are moderators that can upload slides. Circles are participants. When you're in here, by the way, try to make sure everyone logs in with the listen-only mode if they actually log in. One thing that's nice about logging in is that you could participate in chat and everything else. So I do suggest people log in, but tell the audience only listen-only mode. No one should be hitting the speakers. One thing, it's less hard on the servers. Listen-only mode is very easy on the servers. And the second thing is we don't want background noise. If you put the speakers on, you're going to hear the speakers here, and you're going to have issues with whatever. So that's all I have. Yes.
I see the default slides. We should fast forward before they go, right?
Yes, the default slides. Ideally, this is where the anti-harassment is supposed to be, but it seems like they didn't put that on. So that's our fault for that. We should post anti-harassment. Please, when you start your microconference, do mention that. We do have a code of conduct here, and I don't think it should be an issue, but focus on technical discussions. If you don't like what someone says, I kind of tell people, if you think in your head, well, that was really stupid, don't speak it. Don't say, well, that was really stupid. Then in your head, it's up to you to say, think in your head and say, why do I think that was stupid? And then try to articulate technical reasons to say that this solution does not work. So that's what, try to, in your head, try to put that filter in. I know I have to work hard to do it. So if I could do it, you can do it. Okay. Well, thank you. I'll let you guys get going and upload slides. By the way, you think this was worth it? Yeah. Real quick, is this worth? I would say, is this worth time to have this before the meeting?
Yeah.
Okay.
We always find some books like this.
Okay. So if I were to want John Stoltz here, I could go here. I just left click on it. And it'll say make presenter, promote to moderator.
Okay.
That's what you want to do here. So.
Thanks.
Yep. We have a mic. We should have a look. Yeah, I think that mic. Oh, yeah. We should have
Okay. Hey, by the way, what are you talking about? Oh, that's a big This is totally incorrect. I was on the same plane. I won't even tell you what he
He's got to upload slides, so I'm I just need a presenter.
Steve, and while presenting,
No, but this is taking. Yeah, you're just.
so I can record that.
You can do whatever you want on the laptop, but it's not good. You need this, you can't see it, but you want to be able to read the chat as well.
I don't know if I was reading chat, but
If you want to close it.
nothing. Just wait. Hi. We're just waiting for the time to pass. 2 more minutes to go. We have 2 minutes of flexity. Okay. No, it's time to start. I set my watch wrong last time, and it's 4 minutes late. So hi, welcome to the real time and scheduling micro conference. It's two communities, right? Real time and scheduling is two kind of topics, but at the end of the day, we are mostly the same people doing the same thing. And so it's better to concentrate into a conference with a lot of like hot topics and get people involved. And it's good to see everybody here. There's people that I haven't seen for quite a while. Things are getting back to normal. I think at this time things are normal, and it's like for me it's a special moment of the year coming to the conference because I see many people that I work every day, and I just don't see every day. It's a social moment for us, the people that work in the kernel. We would like to say thanks for the sponsor to make this possible. It's not easy to organize a conference like this, and mainly say thanks for the people organizing it. I know that there's a lot of work behind for the people. Thanks to Steve that is always running for these things. It's a very important for us. And also, the idea here is to discuss, right? For us to express ourselves in a more productive way than we do at a mailing list. We can express ourselves better here in the real life, and that's the idea. If you have questions, ask. If you want to stop presentation, stop. The ideas of the presentation is that they are very short to introduce the problem, so people have time to discuss, and that's the idea. And as Steven said, let's keep a healthy ambient here. Let's discuss, and if things start to get warm before they get hot, let's breathe and let's be kind to everyone. We need to follow the code of conduct, and we need to make like an environment where people feel at their best to discuss and share their ideas, right? At the end, that's what matters and that's what is best. So, and I am the first presenter. Let me. So I'm Daniel. I work for Red Hat, and I'm mostly working on scheduling and real-time and verification stuff on that realm. And I'm here to talk about the patch set that we are discussing. We had a lot of discussions last week, and it's about the DL server as a mechanism to replace the throttling as a first step, then to make it generic. So what is the problem, right? On the regular FIFO scheduler and RR, we don't have a bandwidth control, right? So a real-time task in the scheduler, I think it's the people doing the, it's not on me, I'm just. So yes, as they put this letter full screen. So the idea, the problem is that when you yeah, you don't need to see myself twice. One is already too much. So the main problem there is, or the basic problem is that with on our scheduler hierarchy, the real-time scheduler, the RT scheduler, is always on top of CFS, or of fair scheduler, we should say now. And if one runs a busy loop task, either because they want or because there's a bug, when a real-time task starts running, it will run forever, and it might cause starvation problems for fair tasks. And if it's a user task, it's okay. It's a decision of the user. But the point is that we have a lot of per CPU tasks that are deferred work, and they need to be deferred work. They need to run after some time or when there's some spare time, because that's the idea of deferred work, right? But if they never run, they can cause issues like RCU stalls or hang other tasks on other CPUs. So we need to avoid this kind of problems. And the current mechanism that we have in the kernel is that if the real-time scheduler runs for a long time, for a longer runtime, we have two variables here. If it runs for longer than 950 milliseconds, then the entire run queue is throttled to give a chance for the non-real-time tasks to run. And it was born more as a debugging mechanism, as a safety guard, than like instead of a scheduling guarantee. It's a safety measure. The good thing is, I say it works in the sense that if you have like a deadline not, but if you have real-time RT tasks running for quite a while, the entire RQ will be throttled. The point is that one of the problems, there are more, but is that if you have like an idle, if you don't have normal tasks, then the CPU goes idle and people throw CPU time away. We tried to fix this in the past. Back in 2017, I sent a patch that just did, okay, if there is no starving task, just continue running RT. It worked, but it was a duct tape for sure. We carried it on RHEL for quite a while. I think that people at Google also use it on Android, I think, for a while, but it was a duct tape. At Red Hat, we built a user space tool that the name in Italian, first name was workaround in Italian, and we had to change the name to put it in our repo, but Yeah, and this tool, it worked by, it monitored the run queue, and if after like an amount of time, like 20 seconds or 1 second, if there is a fair task that never had a context switch, we assumed it was starving and it was there. The tool went there and set the temporarily set the schedule deadline parameters. So the task was boosted using the deadline scheduler. Just to refresh people's mind, like in the hierarchy of scheduling, we have the sched deadline on top of RT. So if you put a task on the sched deadline, it will preempt the RT. So we were just boop, bumping it. And back in the day, in 2007, Peter suggested a patch set that was, instead of boosting a task, you could boost the entire fair run queue. So if we have like a fair task, it would run for a certain runtime as the real time as a deadline task. But back in the day, we started discussing it, and we noticed some problems, right? What we wanted, if after some time the normal tasks, the fair task, didn't have a time to execute, we would like to boost it. Why we would like to wait for some time? Because if we just boosted right up on front the non-real time, the fair tasks, if we just boost it, it will always get on top of the FIFO, the real-time tasks. And we would have an anomaly that would be like this. My system is idle. Then I have a real-time task and a fair task being awakened at the same time. If we boosted the fair task as a DL task, the fair task would always run on top of RT. So we would have an inversion on the scheduling priorities. And that would break many workloads. So that was on our intention, and that is what we were having, like the normal scheduler being scheduled like a deadline task. We were breaking the FIFO scheduler. Then on the discussions, we started talking about having a zero laxity scheduler. The intention of the zero laxity scheduler is this: okay, schedule when you have not much time to the deadline. That is the intention. But what can actually have is that when this time come, the normal task would run on top of everyone. And here we would have to enter on the details of this CAT deadline. But basically, at this point in time, if we boost the time, if we delay postponing the task, and we run it when it's zero laxity, the zero laxity is when you are a runtime away from your deadline. Let's say you have a 1 second task, we set it to run at 50 milliseconds before the deadline, and we run it with the deadline at 50 microseconds. But we would have to enter on some details here, but this would break the SCAD deadline, the idea of zero laxity. And I can speak more in discussion. So the idea that we are working now is deferring the activation of the DL server for the fair scheduler for a time in the future, the zero lax time. So the idea is that, why do we want to do that, right? As I said before, the fixed priority scheduler has this good priority, that is, the highest priority tasks start running and it runs if there is nothing higher, right? And many people rely on that. We don't have that on EDF because on the SCAD deadline, because the priorities change over the time. Using the DL server was the best way to get out of this starvation, right? It boosts the RQ, it fixes other problems. But if we activate it when we don't need, we can break the first property. So the idea is that we only need to activate, or only need to boost the normal scheduler when it's starving. If we boost it when it's not starving, we might have this situation where you get a real-time task and a fair task, and the fair task get on top of the RT. I think this would break many drivers and many people waiting on IRQs. And yeah, and we learned with Staudy, that workaround, that waiting for it was a good solution. So the algorithm works like this. Anytime a fair task is in queued, we start it as a scheduled deadline task, but we don't enqueue it as a deadline task. We throttle it until the zero elapsed moment. So we say schedule it after a while. And after this while passes, like if the task is able to run as a fair without being served as a deadline, like if the system is idle, my fair task is able to consume it the runtime it's reserved for it, we will be always discounting the time. And if it was able to get the runtime inside the period, we don't boost it. We reset this mechanism and postpone the period ahead, trying to postpone the time that we will activate the server. If the task didn't have enough runtime until the deadline, we boosted the server. And yes, this fair server, it's always enabled when you have a fair task. It's watching the run queue, and if the run queue has time to consume its DL runtime, we restart the period, and or otherwise we just let it boost. On the current implementation, we have a runtime and a period for the throttling, and it's global. And in this case here, we are improving it by having a per CPU parameters. And you can say also if you want to defer or not the server. There are cases in which you don't want to defer, and then we can discuss this. And the RT throttling mechanism, it's with this patch set, the RT throttling, it doesn't disappear because the RT group scheduling depends on it. But it's confined RT group scheduling option that is disabled on I think most of the distributions. And in the future, we have plans to replace this with a SCAD server, but it requires some deep research. And it works, that famous dashboards. And that's it. Questions, discussions?
Is there anything keeping it from? Yeah, just want to make sure. So what's keeping it from going upstream now, or is it on its way? Is there any issues that's preventing it?
I think we need to ask for this guy. Peter?
Peter on?
It seems I'm hearing him, but very low in volume.
Is if a remote speaker comes in, is the speakers, should we be able to hear it?
Let me see if he's still on.
Do you want to go outside and also test to make sure?
This scroll doesn't work fine here. So I would try to answer
Is
this.
there also check out a matrix server? I don't know if Peter's on matrix at all.
LMNLP. No, he's not online. So this guy is offline. No, Peter is remote. So when he speaks, it looks like the sound from the sky. What I heard from Peter is that it's queued on his Git branch. Peter's queued.git. It seems that it's on the way to be merged maybe in the next release, but I think only Peter can say that. That's my interpretation.
Yeah. So actually, this I make this a question more to the audience because people here may not understand the implications of this. So how many people here actually use like a real-time task for their application? Like they actually put something into real time, a few or whatever. Anyone feel like you should, like there's something that you want run immediately or something and you don't because real-time tasks have sort of a side effect to things. Like one thing is that they go running forever. We have actually a use case in Chrome OS for this because we want, reaction times when you move the mouse, you'll see the video change right away. Games and everything else require this. So the idea is to be able to set things to real time that we normally would not set to real time because we don't trust them. And then have the DL server be there to basically protect the rest of the system. So a malicious task that gets real time can't harm the system because the DL server will kick in and still keep everything moving. So with that aspect of the DL server, is people more likely to use a real time task for various threads? Yes, no? I guess no one here cares.
If anyone is using the real-time, the existing real-time throttling. So the existing real-time throttling, how many users we have, because we are essentially changing how it works.
Who relies on some properties of the throttling to see if we are not breaking it? I think the problem of this patch set is that I sent it last Saturday, so we could have time to reach for people to read the patch set again and discuss here. Yeah, but then we just make it happen the last week.
Yes,
Joe.
so actually, at least in user space, the Pulse Audio and Pipewire guys, they use a daemon in user space to monitor their RT tasks. And if the RT tasks actually exceeded like 200 milliseconds or so, then they kill it and so on.
Yeah.
So, and it is a debug service basically, and they do some ugly hacks to do it, but they have, it is actually in all distributions.
Yeah, so they have their homemade way to avoid the audio threads to starve the system, right?
Yes.
Yeah, that's same thing we do with this Taudi. Now they can just set the parameters on the SCAD server per CPU, and they can even pin their tasks into a CPU and change the parameters of the L server only for that.
I was just going to say, like, there was a question about who uses RT throttling, and I was going to say the obvious thing that everybody, right? Because otherwise the system will hang. So, yeah,
So-
but
We
already,
we have it at Red Hat. Many customers they want to run like a CPU full time, and because there's no full isolation, completely full isolation, they don't trust on setting the tasks as fair tasks. They boost it to deadline, to boost it to RT, and they every once in a while hit the starvation. Crystal has a question.
Oh, wait, yeah. Did you want, here,
Okay, setting a user interface thing to be SCAD FIFO, and then just relying on this thing to keep it from just running over everything seems a little backwards. I seem to recall, you may recall a couple decades ago, this thing called CPU reservations. The idea of having some way of saying, okay, this thread does need to have some RT bandwidth, but cut that thing off, not all RT. A more fine-grained thing might be more suitable for that.
Like SCAD deadline. Absolutely.
Well, one thing is I gave a talk at OSPM. The problem is SCAD deadline is it's very hard to use. And another thing is because worst case execution time is something that's basically impossible to calculate. If you were to calculate it, you're going to get something huge, but because of caches and everything, the range of when things run. I mean,
No, but that's a pessimistic view of that. You don't need to set it as a worst case, because the CBS
yes,
works
but
as
still the thing is you don't want it to be throttled unnecessarily. So the well, what's it called? There's another thing I was
The
going to
grub?
say. Was that
grub.
grub? No, grub does help with that. But if something is running, it's not going to run. So maybe you do want to extend it. So you do.
Now,
Like, that's the thing is, you only want to. I like the fact that we don't want to keep things starving. Now, what would be really nice is if we could have this for RT things where we can make this individual a little bit more fine-tuned. Once we get the L server in to say it can only throttle certain, maybe we can have a way of throttling different things or have different levels, like an RT server that will allow your RT tasks to go.
I think the main wish, let's say, using Peter's words here, the main wish is to get out of the RT as the FIFO scheduler, and try to make the SCAD deadline more suitable for the workload that people have.
And I disagree with Peter on one thing. I know I wish Peter could talk, but the one thing I disagree about Peter is saying that there's no use cases. I do believe reaction time use case, the latency thing, where you don't care about period runtime CPU users. When this event happens, I want this thing to happen to reply immediately. That is an RT FIFO situation.
Because that's
deadline.
the property that SCAD deadline doesn't have. You can arrange things playing with the size of your periods somehow in the way that the VDF does. Okay, time is done.
Yeah, time's up. Time's
Oh,
up. But
by the
anyway,
way-
just real quick before we switch off, I want everyone that has a Linux laptop up and running, go do a D message and see if you see RT throttling. I'm just curious how many people have that happening on their laptop right now. Yeah. Okay.
Yeah.
Well, no, everyone has that by all defaults. Okay. Thank you, everyone.
By the way, now SCAD deadline has one user.
Yeah.
We had it because of the way we
Topic
were,
number 2.
because of the way we were using RT, because we were using the
So you can switch
subgroups.
it? Do you know how to switch it?
Not sure.
Which one?
Here, scaling idle.
You can switch this to full screen.
Well, yeah, I
Because
mean,
we were actually, we were trying to use sub-secret songs.
What is this in Chrome?
all right.
That's on my Debian. In Debian, I have an issue.
So let's get started. This presentation is more about the scheduler aspect of the. Should I wait 1 minute for people to?
Okay, we're starting the next one.
Oh, microphone. This. All right.
So you can sit here. I'll move my laptop out.
Yeah, so this is more about the scheduler part of this micro conference. This is so I want to walk you through an investigation I've been doing on my spare time in the past months. It has to do with how the fair scheduler scales, well, not so well on large systems with respect to idle CPUs. So how it all started. So it started by me adding a feature in the Linux scheduler to implement a concurrent CID feature in restartable sequence. But when I did it, I added a raw spin lock on the scheduler context switch fastpath. That caused regressions that were reported by Intel, AMD, and Oracle. I did the work to remove those spin locks and modify the algorithm. But then removing a spin lock on the fastpath actually caused another performance regression on Hackbench. So it was actually faster to take a per task or a global spin lock on the scheduler fastpath than to not have the lock. So why is that, right? So I could reproduce that on a rather large machine with a AMD machine with 192 core over 2 sockets. And that's a Hackbench workload in thread mode, 32 groups, each 25 descriptors per group using pipes, 100 byte messages. And basically, it's an end-to-end relationship of producers and consumers, producers filling pipes, consumers waking up the producers when the pipes are being emptied. So I did several rounds of approaches to kind of get this. So the end result of those improvements is to bring the Hackbench workload from 49 seconds down to 29 seconds. So it's about 40% improvement. So there is room for improvement there. So I gradually modified that global spin lock that made no sense to try to figure out what in that spin lock actually sped up the system. So one of the things I've done is to add a delay loop in do idle. That helped. So I first noticed that this spin lock, I mean, the place where it was actually useful was when context switching to idle. So I modified that, added the delay loop in idle instead. That worked to speed up things. So doing that. I modified that to add a 1 millisecond delay where I would tag the run queue to say, well, for run queue selection purposes, consider this run queue as if it was idle. That also sped up things. Then I went with different approaches. So the idea there is, I mean, that's one workload. The problem is that this can have ill effect for other workloads, right? As soon as you tweak something. So another approach I did take was to favor almost idle previously used CPUs for wake-a-fine, skipping queued wake-ups when the L2 is shared, because I noticed that there was a high contention rate on the run queue lock. So using queued wake-ups helped there. It also changed a bit the wake-up patterns. I took different approaches, trying also to rate limit task migration. So I added basically some features that would keep track on a per task basis on when it was recently migrated. So I did that. Biasing the run queue selection towards previous CPU is the latest things I've pushed so far. And this is where, so Hackbench workload speeds up for 40%. With perf stats, I could see that the migration rates kind of lessens when I do those changes. Each of those different approaches are different ways to get that speed up. And then, for the latest approach I took, which was to bias towards the previous run queue, it did have a performance regression for client-server workloads, where you have a one-to-one relationship between the client and the server. So the latest things I've worked on for the past few weeks. Okay. First, so I come to realize that one of the issue there is that the Linux scheduler is very trigger happy about moving tasks to idle CPUs. So it wants, as long as there's work to be done, it wants no CPU to be idle. But the problem is that this can cause run queue lock contention, and this can have cache and NUMA miss effects on the workload memory patterns. So on large system, that can become increasingly a problem, because then you have much more chances to have some idle cores. The more cores you have on large systems, the more, the less locality you will end up having. And the reason why the Linux scheduler does that is to try to be work conserving, so that on a system with n CPUs, the n highest priority task would be all running. So that would be the real-time definition, but I guess it's kind of somewhat applied to the fair scheduler to try to fill in the idle CPUs. So what I've been working on for the past 2 weeks. So it's a task placement algorithm that I'm working on. It's a it's a prototype, right? Work in progress. So, because, one way to solve this one-to-one workload pattern would be to create yet another heuristic. But I find that the fair scheduler already contains a fair amount of heuristics. So I would like to maybe lessen that and try to step back and look at the overall general problem. So what I'm trying to achieve here is to look at a problem from a communication pattern point of view. So basically, what I've created is a predictor. So I keep, on a per task basis, I keep a predictor, which is a set of counters that counts the amount of interactions between wakers and wakees based on the topology of the system. So if I'm a waker and I wake up someone else, I sit on a specific core on a specific L3 cache and on a specific NUMA node. So this is where I am in the topology. The wakey also will be woken up somewhere in the topology. So I increment counters based on waker-wakey relationship to get an idea of how much internet connection a given task has with respect to the hierarchy. And my end goal is to converge the task placement so that the tasks get moved together as close as possible in the hierarchy when they interact with each other. So it actually seems to work well. It's not completed yet. I will show what is being done, has been done. So the goal is to really converge towards a task placement that's based on the communication pattern. So here I will discuss a little bit about the run queue metrics. So in the Linux scheduler, so we have the per run queue utilization, runnable, and load average. Utilization is really, so for all the tasks, including the sleeping and blocking tasks, this is really the important point. So utilization is the amount of time that is actually used on the CPU for all those tasks that are on the run queue. Runnable is how much they would have liked to run. So if there's overcommit, it can go beyond the available time. And the load actually takes into account the weight of tasks. So it's the runnable taking into account the weight of tasks as well to compare between run queues. So what I ended up needing here, so it actually worked, it did not work. That started for selecting the previous CPU for putting back a task on it, if there's enough capacity left. So it did not work when I used the averages, because they take into account the currently sleeping and blocking tasks. So thinks there's no more room left, but the tasks are actually sleeping. So the enqueued estimate utilization on the metric of the run queue actually works for this, because it really it only considers, it excludes the sleeping and blocking task from that metric. But the thing it does not do is considered the overcommit. So it only takes into account the actual task utilization of the CPU. But if they would like to run more, it does not take that into account. So here I've created a new enqueued runnable metric, which takes into account the runnable time, so the time the task wish to be scheduled. Yes, one question.
One thing that is like runnable is not how much you would like to run, it's how much you are ready to run on the CPU. So that just highlight the contention on the CPU more than how much you would like to run. That's an important point to make. I mean, because you can still have the right utilization, but you will have to wait twice more than what you would like to run. That's really the difference between runnable and utilization.
But then runnable kind of gives an idea of the amount of overcommit, right?
Oh yeah, that's really show the contention that some tasks can have on the same CPU. The runnable is there to say we have several tasks fighting for the same CPU.
Yes.
And that will increase the runnable to show this fight, in fact.
Yes, yes. Which is actually a nice characteristic and something I want to be taken into account. Yes. Because I tried my algorithm with the predictor with the utilization, and it packed so I had like 384 hardware threads, and it was packing all my tasks over 10. So because it was thinking, oh, okay, it's not used too much, but no, it's the utilization. So even if it was based on the slice they had, not the slice they would like to have.
It's not what they would like, but because they probably don't want more. It's just that they will have to wait to run. And I mean, you might need only 1 millisecond, but if you are 100 thread waiting on the same CPU, you can wait 100 milliseconds, which is quite huge.
Yeah. So, and thanks for correcting me. By the way, I mean, this is really, in the past month, I have started learning how the fair scheduler works. So some of my understanding might be wobbly, so that's good.
One more question. How do you track the relationship between wakers and wakees? Can it be any task, or how do you track? Because it can be many tasks and you probably don't know which tasks are interesting which.
How the predictor is implemented, you mean?
Yeah.
Yes. So the predictor here. So it's a set of, so those are counters that are per task. So I have an array of counters within the task for every core on the system. And those counters are single byte counters, right? So they accumulate up to 255 and they saturate there. They're all saturated counters, and they try to take as little space as possible. So they count the amount of interactions waker-wakeys on a per core basis, on a per cluster basis, and on a per NUMA node basis.
So it's per core, it's not per, you're not tracking any random wakey or waker.
Yes, I mean, if there's an interaction between a waker and a wakey, they will increment the counters according to the topology of where the waker and the wakeys were located when the wake up happened.
Okay.
In both the waker and the wakey. So you know you have a connection point there.
Okay.
Sorry, just want to interject, maybe there is not a lot of time, but I just want to raise the point that, coming from Android world, where we really deal with a lot of general purpose stuff, I find this tradition of continuous to add heuristic, as you said, we don't want to add another one, is just not sustainable anymore. And I'm thinking, could we try to solve the problem by potentially try to think how we can rewrite programs differently, so that if Hackbench, for instance, or something similar needs to be packed, which I think the kind of characteristic you're looking for, these tasks really would like to stay on the same cache level. That would be a better way to try to handle things, so that we can start moving towards more things that can be portable, work across any system.
So applications could give hints about task placement.
Having more hints, basically.
Yeah, that could help as well.
So instead of trying to solve it at the kernel level.
Yeah, actually related to that, I was actually wondering if we could, if you could achieve some of this by clustering your system. So if you know more or less how many CPUs your application needs, then you do some clusterization, and then the scheduler already kind of knows the boundaries better than the 300 plus CPUs available.
Yeah. But in this case, the workload is using the whole system.
Okay. Okay.
Yeah.
Depends. Yeah.
Just one thing that we discussed, in the past we discussed is wake-up heuristics. And it seems that the best way to try to follow is not trying to follow wake-up heuristics, but moving things to the load balancer and try to address these things before the wake-up. That was the understanding, I think, from 4 years ago.
Yeah, and I'm coming to the load balancing part. Actually, I still have 4 minutes left, so I guess I'll just maybe one more question.
Yeah, one more question. So if I understand correctly, this speeds things up or reduces latency. Have you looked at the power side of the ledger? Like when you do this, you're trading off performance versus possibly higher power. Have you taken a look at what this trade-off looks like?
Not yet. That's a good point.
Thank you.
I think in last years we had talks, I think Julia speaks about this, that if you pack things on fewer CPUs, you can reach more power savings. There is knowledge people. Just can you turn to Julia? You're closer.
Yeah,
Okay,
so the point-
can you stand up so camera can see you? If you don't mind.
So the point of my talk was that if you pack them on fewer CPUs, then those CPUs will have to run at a higher frequency, or will get to run at a higher frequency, and then you'll be able to finish your application sooner. There's also the whole cost of the encore, and that encore is going along the whole time. And so if you actually finish sooner, then you can actually save power with respect to your application.
Research, just wait for the.
But this is only true for a particular system with a particular workload. From what I've seen, the same workload with the same characteristics, move it to a different system with different like DBFS, different like CPU cores, you will get the completely different results. So we cannot generalize from like one aspect. You really need to go across the board. It's really hard to make sure it's actually completely true.
So I will quickly describe the backtracking. So this is the backtracking. So we start from the core down to the NUMA node to try to find somewhere there where there's enough capacity to run. I'll skip over that. Current result, that's my last slide actually, because I'm out of time. So with this approach, mainline kernel has 40% idle on all CPUs. With the current algorithm I have, on node 0, they are 10% idle. On node 1, they are 66% idle. So I have remaining room capacity left. So I think what I still need to do is integrate with task balancing algorithms to kind of use the predictor shape as a pattern to group tasks together and in one go move the task to node 1. So basically, because I think what is happening now is that there's so many tasks on node 0 that they all get pulled back on node 0 all the time. So which is why they have a hard time migrating the whole group to node 1. But yeah, I mean, that's it. That's what I have.
I think you're 1 minute. Yeah. One last question. One short question.
Yeah. So do you know exactly what make the performance improvement? I mean, is it really having the two tasks closer on the same CPU or the same SMT, or is it the fact that you're not waking up some...
I'm not sure about the cause, right? Yeah. What I observe is that the number of migration drastically reduces.
Yeah.
And the other thing is, I'm not sure I'm looking at the correct metrics in terms of stalls and cache misses and so on and so forth, because I could not find something very, very much like, oh yes, this is like 15, 20% difference, right? But I figured there might be something about the communication. Being closer might be better for the group. So, and this is my goal. I want to group the tasks that communicate together as close as possible in the topology of the system.
Thank you, Matthew.
Thank you.
Check normally there. can start now. Okay. Hi, everybody. So,
Hey, next, it's starting now.
my name is Vincent Guiteau. I'm working for Lenovo in the kernel working group, so mainly on the
People,
scheduler.
please. Low volume.
And today I'm going to speak about system pressure and CPU capacity, which is mainly the fact that so system pressure and CPU capacity is mainly about the fact that even if you have some powerful CPU, most of the time you can't use this highest compute capacity all the time on your system, and how you can reflect that in the scheduler so that we can do a better task placement or load balancing. So that's something I discussed at OSPM 6 months ago. So that will be mainly a kind of a update and follow on what is going on. So, yeah. So what does impact the compute capacity of a CPU? So that's just to highlight what can make a CPU less powerful than it could be. So there is mainly two parts. One, it's about stealing some CPU cycle, and I will not speak about that for today. I'm really focusing on the CPU performance, which is mainly the frequency scaling. So, and for that, we have several things that can impact the frequency of a CPU. So, and I have tried to sort that between high frequency up to almost stable or all the time there, impact on the CPU capacity. So I have sorted that in three main parts. The first one is really what we call high frequency scaling on the CPU frequency. So, and this usually happen, you usually have some hardware IP running on beside your CPU that will scale the frequency of your CPU at kilohertz. And for that, the scheduler can't do anything. It can only, at the best, get the feedback about, in average, how much compute capacity is available. But you can't really say what will be the frequency at the time you will make a selection. So you can't really say, okay, the frequency is 1 gig, so I can put this task. Because by the time you are selecting the CPU, maybe the frequency has switched back to only 500 or goes up to 2 gig. So you can only rely on average. Then we have few other things, and more either in the kernel with the thermal framework, for example, or with the power capping or things like that, and even inside the firmware where you can cap the max frequency of a CPU for dozens of milliseconds, hundreds of milliseconds, just because there are some thermal limitation, or just because from a power management point of view, you don't need all the maximum throughput of your CPU. So you don't want to waste power just because that doesn't work, I mean. And the last part, it's mainly the user space. So we have the CPU frec scaling max frec interface, which is mainly capping the frequency, and that's used by some distro. And that's the same. It's usually used when you want to enable power saving on your system. So on your laptop, for example. And in this case, you know that this will be applied for seconds at least, or hours, that depends. So we have three main things. Something faster than we can track, something that we can take into account for the next 10, 20, or 100 milliseconds, and something that can be seen as always there. So based on that, I have tried to enable new interface in the scheduler, or at least to rational what have been done so far. So the first things, and that's something that is under discussion on the mailing list, and I think we are close to have something, I would say, ready to be queued. So that's what we have right now. So in the scheduler, we have the R-scale CPU capacity, which reflects the max compute capacity of your system. We have an R-scale thermal pressure, which reflects which kind of thermal pressure is applied to your system. And we'll see that this one can be used in several places, in several ways. This can be used by some hardware IP capping the frequency at higher rate, and it's also used by firmware sometimes. So we have this signal which is used by two different kind of system, and on which we'd like to apply two different kind of behavior. And then we have on the other side, and it just so we are able to know what is the current scaling current CPU capacity based on the current frequency. And this is based typically on the scaling current frec, even if it's not really true now that we have this hardware counter that can just reflect what is the real frequency of your CPU for the last tick in our case. So that's almost what we have. And you can also notice that the R-scale frec, which is the frequency which has been used to say this is what I consider the max compute capacity of my system. And it's not CPU info max, mainly because in some system, the maximum frequency is not sustainable at all, which means that I think it's an Intel platform, the turbo, can be sustainable for a few milliseconds maybe before overheating. So the goal there is really to say this is what is available for your system to play some task. So the first one that was mentioned is that the user space and distro typically can scale the maximum frequency of your laptop, depending if you are plugged on the wall power supply or not, for example, but not only. I know that some of the distros sometimes are capping the frequency just because they know that what's going on the CPU doesn't need the highest compute capacity. You don't care, running at 2 gig if you're playing some MP3 playback. You don't need that. But if you don't do anything, in some case, the scheduler, the frequency, the CPU frec governor might say, okay, it's worth jumping to 2 gig for 1 or 2 milliseconds. So the goal is to get this value, so the scaling max frec, which is feed in the frec QoS request. So the goal would be to feed that back in the scheduler. One can say that we could use the R-scale CPU capacity, which is what we have right now in the scheduler. And because if we consider that this will stand for 1 second, 1 hour, 1 day, maybe that could be good. Except that this value is also used in other places in the scheduler, like the PELT, the load tracking mechanism. And doing some switch can create some strange behavior. Yeah, one question.
Quick question. So why is it that we can't reuse R-scale CPU capacity? Can't you figure out the min of whatever's the R-scale capacity and max freq request to set it?
Sorry, what?
Why can't you reuse R-scale CPU capacity?
Mainly because, for example, if you're looking in the load tracking mechanism, you want to scale, because you want the load tracking mechanism, you should have an utilization, which is agnostic on which CPU at which frequency you are running. So you always must be able to scale your current utilization in something that can scale in the full compute capacity of the CPU, for example. That's one reason. And there was another reason there, and it was, in a big little system, you are using EES. And in this case, on one side, you have the frequency, the CPU frec governor that will scale. And on the other side, we have the energy model. And both need to have the same range. So typically, if I'm going up there.
I think I got the idea.
Yeah, you got the thing. Yeah, you need to keep this. These are just the max available at any time. Okay. So the goal would be to add a new interface, which would be R-scale CPU cap, which mainly say this is the current capacity, sustainable capacity that you can get for the coming seconds. The goal is really to say you don't have to take care if that change over between two ticks, for example. So far, so the patch I'm working on are almost ready. From what I have seen, there was 2 parts. I have started to look at each and every place where the R-scale CPU capacity was used, and should we use this original maximum capacity or the current sustainable capacity? And it's used in several places, including the deadline server, for example. And I think that's another thing that was wondering, because in the deadline scale server, for example, I think that in some situation, we would like to know what is the maximum available compute capacity for the deadline bandwidth things. And in some other place, in some other case, you want to know what will be really available for the coming second when you're placing tasks. So that's why we need some. So, but most of the time it's quite easily to make the decision. The only things that could be of a problem, but I don't think so, is the misfit task detection right now in the scheduler for the EES. We have a way to find if there is another possible CPU with more compute capacity. And I need to figure out that, but that would mainly be that right now we might have some tick going on regularly because everything is capped to a lower compute capacity, and we need the most powerful CPU. So that gives us a new metric that can be used by the scheduler, which is the R-scale CPU cap, or R-scale CPU capacity cap. I think I made a mistake. And the goal is to link that to the scaling max frequency of the SysFS. Then we have the third type of pressure on our compute capacity, either by the firmware or by some kernel framework like the thermal framework or the power capping, things like that. And for such a case, because we can have several systems applying a pressure, so we need to handle all these requests. We need to get the maximum pressure applied on the CPU between all these requests, which is quite similar to what the frequency QoS max is already doing for CPU frac. So that might be a good way to get all this pressure quite easily. I mean, instead of redoing another framework that will aggregate the max, that will take the maximum pressure on all the requests. And most of the systems that are applying pressure are using this already. There is only few problem with that right now, is that we have some blocking notifier with this feature, which might be a problem in the case of the scheduler, which means that right now, each time you're changing the maximum compute capacity, you have a blocking notifier that is, you are calling all the notification callback that have been registered, and they are non-blocking notifiers. So they can schedule, they can sleep, and they can schedule things. And one of the things is that typically what happens at CPU frac level is that we are scheduling a work to handle this update of the max frequency. Yeah.
I've heard some feedback about recent hardware, basically bringing down the frequency of the front side bus due to power limitations without letting the kernel know about it. So how do you handle that? And do you need more information to kind of correctly handle this?
So typically that would be interesting to get this feedback in the scheduler. So the goal is to provide the infrastructure, but clearly I will not be able to connect that to each and everything. We have few connections. Typically we have a Qualcomm hardware IP, which is called LMH, for example, which is connecting. So it typically, I think it can scale at kilohertz, the frequency, and we have a feedback on that. And then I would say it's up to each and every system that impact the frequency to feedback their pressure.
Matthew, if I'm not mistaken, you're talking about FSP. It's almost like a interconnect, right, to the DDR. You can think of it that way? Okay. That's a whole nother can of worms that we need to take into account before the scheduler can react to it. Let's just get it first working for the CPU, because I don't think it even works for the CPU today. That's what he's trying to say.
Yeah, okay, that's for the interconnect.
Because like lots of other things that need to work for that to work, right?
And so, and also with this new input, we can dedicate the R-scale thermal pressure, which was used by everybody for different reasons. We can dedicate that to the hardware mitigation only. So that will make a clear boundary between.
Another really quick question. When you say kernel pressure, what do you mean?
The kernel pressure is the thermal framework in the kernel. For example, the power capping and DTPM, which are capping that. I mean, and the firmware. I mean, I know that in SCMI we have the power capping interface in SCMI, so the firmware as well can do that, which gives us yet another input, the CPU frac get pressure. And that will be the third one available. And the goal is to use all this in the scheduler, in ES or not. Right now, typically, the ES can get a good use of the CPU frag get pressure and mainly this. And based on that, we'll provide in the scheduler, but that mainly that in the scheduler at some point, if you need to know how much compute capacity is available, so typically you need to get the lowest between the large-scale CPU cap, so what the user space has cap, the FracQoS request feedback as well, so all the firmware, which kind of pressure they can put, and the thermal load average, which is the average of the large-scale thermal signal, which is the high frequency signal from the hardware.
So,
yeah.
For the thermal average, we had that discussion about like the instantaneous and average. Do you plan to keep the average like versus the instantaneous?
So we will keep this one. So the goal is that page up. The large-scale thermal pressure would be renamed large-scale hardware pressure. So if you have an hardware that mitigates at a high frequency, you need to average the signal to get an average pressure. You can't do anything else. So we'll keep that only for that.
Okay. So
then we'll use the CPU frag get pressure, where I'm using CPU frag get pressure because for now, most of the capping applied on the CPU is coming from CPU frag. So that typically where some firmware or some other thermal CPU frag, Linux framework can get. And then we have also the feedback from the user space for the large-scale CPU cap.
So are we supposed to be using different interfaces now, or like is the get pressure is the ultimate interface?
So that will be a new interface that I will provide to the scheduler, the CPU get.
And it will trap the other one, or like are we going still to be using them directly? So like
that's why I would like to provide a function that will get the minimum of all these three.
Okay.
Hey, Vincent. So I just wanted to mention another kind of pressure.
Yeah.
So this is like it came up recently where we see within a VM, we see that the scheduler is not aware of the host physical CPU contention. So it thinks that CPU is a good candidate and it puts a task on it, but on the host side, it's not ideal. They might be better. So there's actually Masami is looking into how to communicate that to the guests, similar to the vCPU's preempted stuff.
Yeah.
So that I was wondering like how that can fit into this, and if there's any.
Then that you can fit that. I would say that's probably we have some interface available right now. So typically we have some virtual interface like SCMI. I know that I'm promoting that in several places. In SCMI, you can get a feedback about the max CPU frag limitation to the VM, for example. So that's doable. I know that there are some other solutions as well done by Saravana about the CPU frag and so on. So maybe they have some other solution.
Sorry if this was already stated, but what are some real world examples of firmware pressure?
The DTPM framework, the CPU frag cooling device is one. The SCMI as well can do some thermal mitigation. The SCMI it's a firmware running on a small CPU that will manage all the power management of your system, including the frequency and so on. So usually they can do some frequency mitigation at higher frequency that the kernel can do, and they leverage that and only say, okay, I will cap the CPU frequency for the next 10 milliseconds, for example, and that's it. And from Intel, I'm pretty sure that there are something similar, but I'm not aware of that. And they can feedback that as well, because that can help quite a lot. Okay, I think it's over.
Testing, 1, 2, 3. Take this one over here. How do I get out of this one and into the next one? Yeah, help me. Yeah, perfect. All right, maybe full screen. You guys come on up here. Ricardo and Vibe. I'll use this one and you guys can use that one. Ready to go? I'm Lynn Brown. This is Ricardo Neri, Vaibhav Shankar. We're going to talk about optimizing Chromium. This is sort of a follow-on to a talk we had last year. Uses some pieces of that, which you may see familiar. Now, how do I go? Okay. The output of the discussion in summary from last year was Vincent said, show value, and so that's pretty much what we're here to do today. We'd like to acknowledge Johnny and Gia on Chromium and Srinivas, Rui, Noor on, I'm going to mention a thing called low power mode daemon, only to contrast it to what we're doing here. There's a whole talk on it in this room tomorrow afternoon. I encourage you to go there. It actually uses also CPU isolation, which I think there's a talk on a little later in here today. And Tim Chen and Chen Yu and Raphael for direct help with some of the scheduling stuff that we've done. All right, so this is sort of a decoder ring of the hardware that we have. The blue boxes are CPUs. Bigger boxes are more powerful CPUs. Intel calls them P cores and E cores. I'll try to use that language. The P cores are sort of double wide because there's HT. Other things to know about them is, unlike an ARM Big Little, they have a significant overlap in their performance profiles. So those E cores can run quite fast. They can use quite a lot of power, not as much as the P cores. And the P cores can run slow and become quite power efficient, but not quite as power efficient as the E cores. What we're really focused on today, I think we're actually in a very good place on the performance part of this puzzle. ITMT works extremely well for that. What we're trying to do today is harvest, in particular, the operating point where the E cores are running at low frequency and they're in an efficient place where the P cores cannot get to. Let's see. Also, we're depicting tasks here in orange. So you've got a fully idle CPU would be all blue. Partially idle is, sort of half used. And then this guy that's filled in would be fully busy. And then the guy with 3 tasks on there would be a run queue with what's running is on the bottom. We'll come back with some examples of this. In fact, here's one now. Okay, so the way ITMT works, if you're not familiar with it, is basically it's implemented exclusively in the idle load balancer. It's quite simple. There's a priority per CPU. Priority is based on our systems, on the maximum turbo frequency. And yes, we can do it for more than a millisecond, Vincent. And in this case, a P core wakes up and says, hey, I'm a higher priority CPU. Who can I help? Oh, look, here's this poor lower priority CPU. We're going to migrate a task, in this case T2, off the back of the run queue from busy to destination. The reverse also happens. So destination can be an E core pulling off of an HT sibling because we get more throughput that way when we run on an E core. And HT sibling is the is the lowest priority CPU in our system. All right, so aside from task placement, an important knob that we have is called EPP. It stands for Energy Performance Preference. And it comes with hardware P states. HWP is how we do P states for the last several years on Intel. And if you could grab me my water bottle, that'd be great. It's an architectural interface, which is important, which means it's enumerable. We don't have to do any model-specific work to know that it's there. However, its weakness is that the actual value that we plug into this register to say, do we want performance or do we want power? The value we put into that register is model-specific. So if you ever see somewhere, and you will, where something is plugged into that register and we didn't check a model number first, that's a bug. All right, so how do we turn that into an interface that's actually usable by something that doesn't want to check model number? Srinivas maintains the Intel P-state driver, and hopefully that's legible, but it has a couple of words. It has performance, balance, power, and power. Performance means I only care about performance, I don't care about power at all. Power means I care about power only, and I really don't care about performance at all. The other two are in the middle. And that gets translated by the driver into the number that we plug into the EPP register. In this case, it's a per CPU property. And as you can probably guess, that has some limitations. So one way it's used is, say, on your Ubuntu system, you have this dialog called the power mode, and it says, hey, I want performance, I want power, I want something in the middle. It comes around and in Splat, it writes EPP on all CPUs to the same thing. And it doesn't change it. That's okay for some things, but it's not okay for other things that we're going to talk about more. If all the tasks are the same need, you're good. Or if you're using the per CPU interface that I showed a second ago for the driver, not this power manager, you could say, hey, I'm going to bind a bunch of tasks here, and I'm going to set their EPP to that. They're good. I'm going to bind a bunch of tasks here, and I'm going to set the EPP to something else. That's good. It's just that this isn't really how people generally use our computers. And now I'm going to pass it to Vaibhav, who's going to talk about the software we're running.
Thank you. So I'll be covering, the main question that was asked, what's the value proposition of, using EQS and how it can basically help, the Chromium browser use cases. So here in particular, what I'm going to show you is, two popular use cases for low power on Chromium. One is video streaming, and the other one is basically video conferencing. So these are two popular use cases which people, generally use for for low power. So if you look at, the low power KPIs, I want to demonstrate the value prop, using, the following experiments. One is, what's the impact of SoC power by using EPP, task placement, and what's the effect of combining, EPP and task placement. So let's start with the first use case, which is basically, the video streaming part. And here, if you look at the CPU utilization for video streaming, it's very close to idle. So you're just doing simple decode, and you're just, sending the frames back at a particular cadence. Say in this case, I'm trying to run a YouTube clip, which is basically a 1080p 24 FPS, clip. And what I'm trying to see is, with the current ITMT scheduler, you always compete for the P course, right? So which is, always high in power. So for this kind of workload, what you generally want is, you want to always pick the efficient core, which is, ideally in this case, it's E core. And by using E core, I'm going to demonstrate, with different power models that we have, what are the power savings that we get.
Right there.
Okay, so this is the first experiment where we apply, EPP across the system. And if you compare, if you look at the default one, and when you compare the other EPP settings, which is performance and balance power, you can see that with performance kind of EPP, you're almost at 2x power. So you're burning a bunch of power for delivering 1080p 24 FPS kind of video playback. And then once you set balance EPP, you can see that I'm able to save roughly 16% of power, compared to the default.
So for those of us who are not too familiar with the Intel architecture, this EPP basically trying to affect how the firmware scales the CPU frequency? Is that what it's doing?
That's right.
Okay.
So you basically tell the firmware how aggressive you have to be,
Okay.
or how power.
I have more thoughts on this, but I'll let you continue. On
Sure.
that. Thanks.
Just in this case, it's only about frequency scaling. The only impact there is.
Yeah, current EPP, you're just applying EPP across the system, and you're trying to see, are you oversubscribing the CPU frequency, or what you're doing, and what's the impact on SoC power.
Keep going.
Okay. And this is basically binding things on various cores, and you can see that if you run video streaming on one cluster, you're able to save 19% power savings. And this is basically the effect of combining both EPP and task placement. And you can see I'm able to save roughly 26% compared to the default, right? And which is a big power savings. And so just moving on to the second use case, this is video conferencing. So here I'm basically simulating a 1080p 30 FPS encode decode scenario. And in this case, Chromium browser is basically using software encode and decode because there are several options that we have and several browsers. So based on the features available, you basically offload it to the hardware or you do it on the CPU. So in this case, it's software encode and decode. And the utilization here, if you look at the CPU utilization for video conferencing, it's basically at a moderate level. And as you add features like background blur or relighting and camera framing, the utilization can vary all the way from moderate to high. If you look at the first experiment of EPP, you can see that when I basically apply balance power, I can save 70 to 72% of SoC power compared to the default. And this is basically highlighting frequency oversubscription problem that we have. And this is the next experiment of task binding. And if you basically run the same Chromium threads on E-cores, you're able to save roughly 32% of power. And in this case, you're just combining both EPP and binding together, and roughly you're able to save 72% of the power compared to the default. So let me just pass on to Len here.
All right, so this begs the question, can you basically do what ViBIF did manually, or what Power Mode does manually? And the answer is sometimes yes. But it has some limitations. So when does it work? It works for low power mode. There's a chip that's coming out in a couple of weeks called Meteor Lake. In this case, we can basically turn off the compute die and run everything over in the corner on a couple of small CPUs. Works very well there, but that only works when you're very close to idle, when there's really no chance that you're going to impact performance. This is implemented in low power mode daemon, and we'll talk about that tomorrow. But is system-wide orchestration the answer? Sometimes no. And when it's not, the answer is when you get into an oversubscribed situation. And briefly, whoops. And so here's a picture of one. So here we're running a couple of things, all which want, I want video over here, I want sound over here, I want, interactive over here, and then you've got 100 other tasks, and they're all mixed into the same soup. If you treat them all together, somebody's going to fail. Eventually, you'll add enough load to the system where it will fail. And so this becomes a game of differentiating between the threads that really care about time and those that don't care about time, okay? And now we'll get into solution space, or at least prototype of solution space. I'll hand it to Ricardo halfway through. So the way Chromium works is it can classify tasks and it can differentiate those tasks for us, okay? And then what we just did is we plumbed it through sched_set_adder, thank you, Peter Z. And then we put a flag in the per task structure. And I'll let Ricardo describe what we do in the kernel.
Yeah, essentially for the kernel, what we are doing is we are adding a new attribute for in task struct that can be, that essential applications can use to define what level of QoS they require energy-wise. This interface, architects can implement this interface in however way they wish. It's very implemented. In the case of Intel, we link this QoS level with the 4 levels that Len was describing. And when we switch from one task to another, we read that parameter and we change it in whatever driver or whatever the architecture needs to do. In our case, we change the EPP value that Len was describing in the beginning of the presentation. So that level changes. Every time we switch to a task, it changes on whatever is the preference of the currently running task. So that works on all of the CPUs, but we also can leverage the differences in the VF curve of the and the performance and power curve of CPUs, which are different for P cores and E cores. And what we do essentially here is a sort of reverse async packing. For Intel hybrid processors, we use ITMT, which essentially traduces itself onto the scheduler as async packing scheduling, which CPUs have priorities, and when a CPU is going to become idle, it will pull tasks from lower priorities. So what happens here is that we have now flow towards higher priority CPUs, which in this case is T1. This is a regular task with maybe a performance biased preference of quality of service, and it will go to higher performance CPUs. In this case, are the big CPUs. And then we have here an energy efficient task in which we do the reverse. A lower priority CPU, when it goes idle, it will find that task and will move it to a lower priority CPU.
Just ask a quick question.
Question? Yes.
We have to skip the question because we need to show the punchline. Yeah. Hang on. Hold your question. Yeah.
Okay.
If we only have 3 minutes, then we have to show the last 3 slides.
So what we have here is essentially how it looks here. What we have here is as tasks start running, they go to the big CPUs and then to the E cores and lastly to the HT siblings. Here is the reverse. We have a key here number of tasks of energy efficiency, quality of service, and they start populating the E cores. And all of the E cores are busy. They start only then they start going to the big CPUs. And yeah, this is your part. Bye-bye.
Thank you, Ricardo. So this is a small demo that we did, or a POC that we did, using the Chromium browser, where we implemented, the EQoS thing. So whatever I did manually in the previous experiments, here we are doing it using the browser automatically. So here, what we are trying to apply is per task EPP, and the second one is EQoS, where you basically say, okay, this is a efficiency task, move all the tasks to the E core. So this is basically done by applying balance efficiency EPP settings.
When Plumbers is about discussion here, not for microconferences, the question has to be asked. So I know you wanted to do this, but still, Plumbers is about not presentations, it's about discussion. You're not here to basically, so that's why I want to know the discussion to go through. If he has a question.
I'm sorry, but we just hadn't gotten to the point yet, and so I didn't know if more questions.
It doesn't matter. The thing is, this is 10 minutes was supposed to be for a presentation, 10 minutes about discussion. I said that you were here.
Go ahead, ask the question.
Yes, please.
We're talking about asking.
Yeah, thanks for that. Actually, I have similar work done in the onboard for the task placement and the DBFS, where the responsiveness of the scheduler, where we migrate too quickly, and the DBFS is basically doesn't take into account, generally the scheduler have a constant response, and regardless you have a very powerful chip or not a very powerful, a very underpowered chip, we have a constant response, and we end up with the effect that you're seeing, where you could save power by not using the frequency too much, but it's attributed to this aggressive behavior. And on the head, the EQS thingy, I heard saying it's related to architecture specific, and I have issue with that, because what we really want to achieve is enable portable software to be written, where it doesn't matter if it's running on Intel, running anywhere else. And if we have to make that QS depend on architecture doing their own thing, I think when the user the application developers wants to use it, they will get very confused. And that will make it really very hard to pick up. And we start creating libraries where we can tell hey, I really don't care what the system is. It's just as long as I
That's a great point. And last year, we started with the architecture independent API. That's actually where this entire discussion started. We didn't really talk about it today, but on top of this, that's exactly what Chromium is using.
Yeah, but I think from the kernel point of view as well, the hint needs to be implemented in such a way that, if the library has to be to know about the architecture specific, we will lose some points.
Great point. Understood.
Real quick, we're going into break time.
Because we have a break time and then.
My view on the whole thing is that Intel is trying to do all of the devious decision in the firmware without taking into account the task details. It's not. It's trying to figure this out by doing CPU utilization. You're trying to do DVFS instead of looking at task utilization. I think that is the biggest problem. All of these problems are basically related to how fast you can react when you migrate. If a big thread migrates, you take a long time to ramp up. That's why you need the performance mode. If it's a little thread migrates, you don't want to ramp up quickly, and that's why you need the power save mode. Start tracking the task utilization, let the kernel handle it. Don't push it away to firmware. That's my opinion on that.
Basically, we can continue. That's what the chats are for. Emails. We continue if you want to present more. Yeah, it's. I think I have to go for break now.
So we'll get back 5 minutes before the end of the regular break. So it's 11 and 11:25, right? Oh.
Check, check. Check, check.
Shows up now. Well, it shows up on there, so I know it works up here. She put the battery in backwards. Now the battery's really hot, so I'm like, ooh, left that going, it probably would have blown up or something. Yeah. She's like, I changed the battery. I'm like, well, you put it in backwards. That one's yeah. I think so.
maybe not. It's usually the outcome. Yeah. So I saw the on switch was on, but it was off, and I was like, "What?" And I opened it, and then it was backwards. I'm like, "How do you?" It tells you right next to it which way to put it.
Just making sure everything's uploaded.
Yeah.
Thank you for doing that.
You're fine.
All right. Yeah, I think so. Couple minutes.
Yes.
I'm doing the Android micro conference, and they've got 3 months there. All right, I might get started here in a second here. So just 25. No, I got 1 minute. Yeah, I'm starting in a minute. Yeah. All right, I might get started in a second here. Folks, gotta settle down. Good. All right, hey everybody. So thanks so much. I'm John Stultz. I'm with the Android systems team, and I'm going to talk a little bit about proxy execution. So there's been a lot of really great folks who've worked on proxy execution for a fairly long time. So I'm just kind of the least of these. I feel like a lot of big brains that have gone into this. So I gave a talk at OSPM in April, and a lot of the stuff I'm going to kind of zip over quickly. So if you're curious for more, you can follow the link for that slide there. So first of all, why do we care? Well, with Android, we really want to be able to enforce the priority before doing foreground and background tasks. We want to make sure those background tasks aren't chewing up the battery, as well as not interrupting the foreground task. And unfortunately, with Android, we aren't able to give kind of untrusted applications real-time priority to solve this. And so instead, we end up with this mix of kind of like C groups and nice values to try to basically throttle the background tasks so that they don't interrupt the foreground tasks. This, however, hits a ton of priority inversion problems. And priority inheritance isn't something that works for sched other tasks. And so just as a result, we aren't able to usefully throttle background tasks without causing a lot of inconsistent behavior for our foreground tasks. And this is kind of a big issue for us. So proxy execution is kind of a generalized form of priority inheritance. It's a very simple idea. Basically, we're just going to track the blocked on relationship between the mutex waiters and the mutex owners. The odd part is that we're then going to keep all of the blocked mutex tasks on the run queue, even though they're not runnable. We're then going to let the scheduler pick the most important tasks between the mutex block tasks and the runnable tasks. If it picks a mutex block task, we traverse that blocked on chain and find a runnable owner and run it instead. So this seems very simple, but it of course gets very complicated. There's issues with these blocked on chains can cross CPUs, so we have to do migrations to basically to the runnable owner CPUs. Additionally, we might have a chain that resolves into a sleeping owner. And in that case, we can't do anything to kind of boost it to run. And so in that case, we dequeue the block task off of the run queue and then queue it onto the sleeping owner's task so that when it wakes up, we can wake it up as well. And there's lots of other complications as well. So the reason why, despite these complexities, we're kind of interested in this is that this is kind of a simple reproducer that I created to illustrate the problem that we see, where we have two tasks kind of doing file system operations, kind of contending on various file system locks. And with vanilla at the top, as soon as we add CPU share limiting to throttle the background task, we start seeing really bad outliers in our foreground tasks. And of course, using proxy execution, this resolves that issue completely. So it's very attractive. So since OSPM, I've sent out 3 versions of the patch series. It's taken a lot. It's been a lot more work than I was hoping. Kind of V5 was kind of the biggest rework of the series. I basically took, the 7 patches I think it was before and split it into something like 40 fine grain patches so I could kind of test each minor step and really try to stabilize the series. Lots of fixes and reworks in that. There's some stuff where I changed things like the return migration. So if we migrated a task to proxy a runnable owner, once it gets the lock back, it may not be able to run on that CPU. So we have to return it back to the CPU it was running on. This was done in the try to wake up path, but it was very racy. And so I just kind of went with a very slow and simple path of just moving it to schedule. So it's one of those things where this gets kind of messy with a lot of locks. This introduced some performance regressions. I haven't gotten a whole lot of feedback. Last week I sent out the V6. This one stabilized the sleeping owner in queuing, which I had left out at V5. And also added some conditionalization on all the logic, so we're able to build it in, but disable it at boot time. Yeah, got a little bit of feedback on this so far, but not too much. Kind of my current set of issues, so the sleeping owner in queuing was really difficult to get right. We end up with this case of we have a lot of tasks sort of enqueued on other tasks. And just in order to do the locking properly with this, we're having kind of a lot of the same top level locks that we have to take to handle this safely. It feels a little bit like I'm kind of recreating a run queue in a way. Additionally, it's super complicated because there's can be mid-chain wake up. So we can have these enqueued owners and something can be woken up midway through, which is kind of unexpected from the way wound mutexes. I can talk a little bit more about that later if people are interested. Again, the return migration, moving it into schedule, it's slow, but it was at least correct. I need to think about how to rework this because we're often kind of running in the wrong order on the locks, or we end up having to kind of swim upstream of the locks for the locking order. And so I need to find a kind of a better approach there, move it back into the try to wake up path. Obviously, sorting out the regression since V4 is a thing to do. And then the other part is at OSPM, we talked a little bit about some optimizations that might be interesting to do, where maybe we could avoid migrations if the owner is actually running on another CPU, and we knew that. Unfortunately, these blocked on chains can traverse multiple run queues, and so we're somewhat limited to how far we can look ahead to determine if the task is running on that queue. And so that kind of inherently limits a little bit of how far we can do those optimizations at this point. So if folks have ideas for that, that would be great. The other big concern I have is just the scheduler is already fairly subtle, so I'm very worried about adding more complexity here. So for discussion, so real practical questions, I haven't gotten a lot of feedback on the series. I did split it up from, kind of 4 to 7 very large patches to, I guess my internal tree is like 40, but I send out about 20. I've kind of compressed them down a little bit. And trying to figure out what's the right level of fine grainness, because I know at 20 patches, that's still kind of imposing for folks to review. Ideas for how to kind of break this up so that we can maybe stage it slowly over time might be a good idea. Any sort of feedback on that would be great. Additionally, don't know do we need to ship it first for folks to take it seriously? I really, just kind of the last decade of my life, I've been really wanting to avoid Android divergence. And so it's really important to the team that we don't do that. But at the same time, this is a really critical issue. Vendors are already doing very creative solutions in their own trees. And we really would like to have a common solution in the near term.
Hey, John.
Yeah.
I was curious, there was that issue where this stuff doesn't play well with RT push-pull. So because you might have a chain that is behind an RT task, you push that.
There's a patch that we have Connor implemented a while back, and as I've been moving through the stack stabilizing things, that's kind of the last bit that I have as well. So I've been working on that recently. I haven't sent it out yet, or at least since V4. But that's a thing I want to make sure it's really solid. But it does. I think it will resolve the issue.
Okay,
so,
sounds good.
So if you're worried about, doing Android like out of tree thing, I mean, if you look at it as something that you're trying to make upstream, at least I know we kind of do this on Chrome. If something that's focused upstream and we're kind of working with the upstream community and we'll say, well, it's working, it seems to work for us, we'll pull it in and would actually deploy it, even though you're worried about, technical debt, but it's not really a technical debt. It's actually more of, it's sort of like the spiral type of development where you're actually kind of working with upstream. Technical debt is when you just fork on something and you ignore upstream at all.
Yeah. One of the issues is that there are, and I would say that would be ideally the case, but it's one of those things where there's a lot of stuff already in the Android tree where I think that was even the original intent. And so once it is in the tree, it becomes difficult to get out because, again, the vendors have their own very eccentric and creative solutions that they're using to solve this. If they start relying on this, it's not something that we can just simply drop.
That's right. That's the difference between Android and Chrome.
And so this it gets very difficult. So it's one of those things where I want to avoid that, but I also want folks to be able to kind of figure out how do we kind of make some movement on this.
Yeah, hi. I feel like your job might be actually quite difficult. So I have some situations I'd like to hear your thoughts. One is, are you still kind of always ignoring CPU affinity when you do this thing? Because there might run into some problems because like some bare metal like applications might have certain assumptions about the cache interference and other effects of performance. Or maybe there's for CPU assumptions. What would you do you think?
So as far as the CPU affinity, so we don't take that into account when we do the proxy migration. So it's that aspect of when we have a lock owner that's on another CPU, and we have an important task that's on a different CPU that needs to run, but it is blocked on that mutex. We migrate it off to the other CPU. It doesn't actually run on that CPU. It just sits on the run queue, and basically is there to boost the task. So it's there for selection, so that we end up running that task. So it releases the lock. As soon as it releases the lock, this task becomes runnable again, and it should migrate back to where it was.
So
the hard part is,
I was just saying, the punchline is as long as you're not running affinity, doesn't matter. No, when you're blocked, you want to proxy someone else. So you get.
Yeah.
Technical problems.
I was saying the affinity is still the one of the lock owner, which is actually taking the other parameters, but the affinity, so the lock owner still runs on the CPUs or on the CPU that is running. We are not migrating the lock owner. We are migrating whoever is donating to the lock owner. So the affinity of who's running is actually maintained.
So it's more like a credit exchange kind of thing. So you don't have to migrate actually. You can just do some kind of credit.
yeah, the task doesn't actually migrate to run on another core. It's just that the task on the run queue, it moves to a different run queue. We don't actually do any running of that task.
Like in theory, you actually don't have to migrate the task. You can just migrate some metrics. That should also.
No, it's not that easy. I just want to say from the task point of view, it doesn't know it migrated.
Yeah,
that's the thing. So the task user space doesn't realize this is happening. It's just an implementation detail. So when you get migrated to another CPU, the task doesn't execute on the other CPU. So the task will never know it was migrated to that CPU and then come back out. It's sort of similar when I need to upload a slide and I have to be presenters. I'll steal the presenter from him. He won't know it. I'll upload the slide and give him back to presenter. He never switched over, but so in theory, he stayed on the same presenter. So
Meanwhile, Steven's done the presentation.
Yeah, I guess it's an implementation trick. I mean, instead of creating, let's say, another RB3 with the chains of the lock chain, we use essentially the scheduler RB3. So you migrate the donors to the same RB3. The scheduler will be selecting a task from, and then let the scheduler select the highest priority, and that one will be used by the lock owner to actually be scheduled. It's kind of an implementation trick, but I mean, the lock owner is not migrating.
I say it's more like a counting or metric trick. Is that?
Yeah.
Yeah.
Why don't we
Okay.
talk some more about it? Because I can get into the details in a lot.
Okay, quickly.
Yeah.
Quickly, the next question is that, like, I think when you dealing with party inversion, you don't want any leaks. We kind of want to cover all the locking cases, all the dependencies. So what do you think about this, like reader-writer locks and maybe multiple locks? This is kind of a graph like a dependency.
So this is another thing that has come up, is that folks are very interested. A lot of the contention that we see where we see the priority inversion also happens on semaphores and reader-writer locks. And so that's an area that I'm going to, after we can get this working stably, kind of see how we can expand it to support those as well. Because
I think Thomas, is he here? Whatever. Or did he step out and not come in?
Yeah.
Because I don't know how complex this is compared to like priority inheritance, but we gave up on reader-writer locks.
Okay.
I mean, seriously, it was just way too complex. It was almost impossible to prove that it was correct.
Right.
So we just kind of gave up on reader-writer locks on priority inheritance. We just said, if you use reader-writer locks, here he is. So Chris, wait, real quick. Yes. So Thomas, the question about he's bringing up is for proxy execution on reader-writer locks. I don't know really the complexity of proxy execution, but if it's compared anywhere to priority inheritance, and we know how that is with reader-writer locks with priority inheritance, we finally just gave up, correct, on that? Right. So yes.
Because of the multiple reader.
Yeah, I mean, GitHub might not be a good option because we have actually I'm dealing with a real world problem. They're involving both C group mutex and C group thread group RW semaphore. So they both kind of getting a party inversion. So if you only fix one, actually the other one will show up. That's like something you don't want to leak, like memory leak kind of thing. So that's something to consider. So we might need to cover everything to get the system work smoothly. Yeah.
Yeah. Watch. Move.
So there's two issues with reader-writer locks. So one is you can't do priority inheritance. I mean, Steven tried and it was an unholy mess and never worked correctly. Yeah, okay, it sometimes worked, but it never worked correctly. So the thing is, the boosting a writer is easy because that's a single entity. But if you have multiple readers, which you want for performance, then having one writer coming in, boosting several readers out is just problematic. It doesn't scale and it gets messy, especially for backing out. So if the writer does a tri-lock, backing out the whole reader side is total horror show. So we had a version where we said, okay, writer boosting is writer boosting readers out is important, so we reduced it to a single reader, which hurts scalability, obviously. So we gave up on that and went back to actually just letting the readers boost the writer and have multiple readers again, which can't be boosted, which is prone to writer starvation. But 15 years ago, when we looked at this, many of the hot paths reader-writer locks were really highly contended, but lots of them, especially networking, moved over to RCU, and the problem doesn't exist anymore. So the only one which is still an issue is MEMAP SAM, the MEMAP reader-writer SAM. But on the other hand, I mean, yeah, if you're doing permanent alloc, de-alloc of, or map, unmap of memory, yeah, so be it. It's your problem. It's performance-wise, it's anyway a slow pass, so it can wait a little bit. It's not horrible. So we didn't see any on the pathological workloads. We didn't see any writer starvation in the last couple of years. So I think it solved it mostly itself by converting it away from reader-writer locks.
I think I only have a minute or two left, but the last thing I just wanted to say is that Sage Sharp had a nice blog post a while back about types of reviews. And so I was going to make a small request, which is, as folks are kind of looking at the patch series, I really would love design, correctness reviews, the polish. You know, I appreciate the grammar checks and things like that, but I just want to make sure that, you know, I want to make sure these designs are pretty solid before going much further. So.
Yeah. So one of the big concerns with this stuff that I had initially was that you have to migrate the whole chain to a CPU, right, to proxy. So the question is, like, at what point do you say that the migration is not worth it? And that's, you know, so if you have too much migration, then you're in this meta stable state where you're migrating all the time.
Yeah.
And that costs too, right?
Yeah. So chain migration helps a little bit, but it is possible to spend a fair amount of time trying to constantly kick tasks around.
So
so that is a concern, but it's I don't know how. So
yeah. Okay.
All right. Well, thank you.
Yeah.
One last. Oh, wait. Just he's waiting for the microphone for quite a while.
It's not more question, more of like really the like in Android we see a lot of starvation issues, and like the solution is really very important moving forward. But it's one of these complex features that highlights that we have a limitation, that sometimes staging something, even if it is not imperfect, it still shows a progress that helps making some, at least in real world. I mean, we still hit corner cases where it will fail, but like it will be less severe than the issues we see. So I would appreciate if there is a way where it can get to a fall where it's not perfect, yes, but it's manageable. It doesn't cause any obvious deadlocks, at least, or breakages, even if there are corner cases. That will really be very helpful, at least to help really products in the real world.
I've tried to
perfection is not really required.
Stage the patches so they're very small. So a lot of the steps, there's often a lot of cases in the early days where if we haven't gotten to that bit of code, we just, you know, basically pull the task off the wrong queue. And so there are a lot of those kind of short outs. So we could kind of start a little bit, but again, I want to make sure people are okay with the whole idea before we get too far. So anyway, thank you so much.
Okay, hello everyone. I am André Almeida from Igalia, and here's Mathieu from Efficios OS, and we're here to talk about adaptive spin locks in user space using RSec. So people have been trying to have adaptive spin locks in user space for a long time, and we are trying to solve this again. Basically, the use case behind that is calling a mutex lock, a contended mutex lock. We eventually call a mutex that requires a context switch, and a context switch can be way more expensive than the critical section itself. And so this can create kind of a micro contention. So you're wasting a lot of time going to the kernel instead of getting the lock. And because of that, some apps like Postgres, they have a complete user space lock implementation to avoid any syscalls. So what we want to do is to allow user space to correctly spin. And a similar use case is that RT mutexes on the kernel side, they use adaptive spin locks, and this has been proved to be a huge performance improvement. So the challenge here is basically how to tell that a user space thread is running or not, because you should only spin if the lock owner is running. And we need a way to do that in a very fast way without any syscalls. And that is where RSAC comes in. So RSAC code is already integrated with the task scheduler and has a fast UAPI. You don't need any syscalls. You can just poke the shared thread, the memory of the thread that is shared between the kernel and the user space. So it's just a matter of reading a structure. And in a similar fashion, RSAC was used for get CPU, and we are seeing a lot of new use case for RSAC that of new ways to user space talking to the kernel and asking questions about the task scheduler. So the idea here is to have a new field for RSAC, like a sched state field. Is updated by the kernel when the process is scheduled out or in. So on that way, you have a field on the user space telling if this thread is running on a CPU or not. So the only thing left for user space is to check this field to ask if the thread is on a CPU or not, and then it can safely spin. Otherwise, it goes to the normal path that is sleeping using mutex. So this is the proposed, one of the proposed structure. Do you want to?
Yeah. So I'll just remove that. The proposed structure, so this is the complex one. The simple one is taking the state in thread ID and move that back right into struct RSEC. So after some discussion with Carlos, so I might go for a simpler layout because, so there's a trade-off there. Either we make things complex like this to have the state information in a separate cache line to eliminate the fact that if it's shared on the struct RSEC, if we have a high contention and we have readers trying to check that state over and over again, then that cache line becomes shared. So if you have a RSEC critical section beginning and wants to store there, that store is slightly more expensive, a few nanoseconds more, right? So there's a slight overhead to having this within the same cache line. But to split that into a different cache line brings extra complexity for all user space users like LPC, for instance, where they have to make room and allocate area for this separate sched state. So it's a trade-off. So there's a slight performance advantage to have an approach like this, where in struct RSEC you have a pointer to a separate cache line that has the state. But
why don't you
microphone?
So why don't you blow up the size of struct RSEC in the first place? No, not via a pointer. Just make it that it's
padding, right?
2 cache lines.
So the problem is, so if I would have additional features to add before that, right, I could pack them into my current cache line and then get to the next one to add this other feature. But if I skip immediately to the next cache line, then that space becomes wasted space.
No.
So,
It becomes reserved space. It's unused at that given point in time, but you can reuse it.
okay, but then I need a new way to expose the fact that the reserved state is not reserved anymore, it's now used. Because so I use auxiliary vectors to let the kernel tell user space how much of the area is actually populated. So if I skip with padding, after that, I need some mechanism to say, well, this padding is not padding anymore. So either I leave that as padding or I need a new mechanism. Yeah. Yeah. Thanks. So that's, do you want to continue?
Yeah. So another concern is about robustness, because this interface requires reading a shared thread information. So the idea here is that user space will implement something that before the thread dies, it will free the lock in the exit path, and we can use the RSEC memory barriers to protect this field before. So we make sure that when you are reading the SCAD state, you are reading something that is meaningful. But we can have these for different process. We can only use these for threads. So the question is this a concern?
Yeah. So if I can just rephrase, so one of the things that we would need for that is integration with libc, so that libc, when it reclaims some thread memory, it issues a RSEC fence through membarrier, so that whatever threads are trying to read that on CPU state from that specific thread's memory, it can use a RSEC critical section to do that load, so that it gets aborted if the memory it wants to read is about to be reclaimed. So that's the idea of how to kind of make things work in terms of this. And of course, because we need to have access to other threads' memory, it only works for private mutexes. It does not work for the shared case, where we have shared memory, mutex and shared memory across processes. That's a current limitation, but I mean, there seems to be quite a lot of use cases that would still benefit from that.
There is a question, Thomas?
Thomas?
So did you talk to the obvious suspects like database people who are so keen about user space spin locks? If they are happy with having it limited to threads? Because I know at least one major database which is not. It's process-based. So you should talk to them, because they might be rather unhappy.
Well, there might be other ways to work around that, but we'd have some way to kind of let threads poke other threads entry. Right. I mean, we want to quickly have the answer of whether the owner thread is on CPU or not. So it needs to sit in memory somewhere, in a memory area that is readable directly by the potential lock takers. And maybe that could be two separate implementations, right? One for the private and one for the non-private.
Yeah, I was about to say maybe you probably, like for the for other processes, you probably need a pointer or something to another shared memory or something that would be able, maybe it could be even mapped always from the kernel to user space. It would have to be set up so you have it mapped so it doesn't get, it's not like RSEC, which I understand, it's just memory and user space, and when kernel wants to do it, it's got to do like a user.
Yes.
So which also question, like, when is the thing set that it says I'm off the CPU? Is it right in the scheduler?
Yes. So it is set currently when the scheduler is preempting the task. So, but it's a statistical hit, right? That store cannot take a page fault.
Right.
So if that page would happen not to be faulted, then it's not doing anything. The state is wrong until it's going back to user space, and then we can take the page fault.
Okay.
But if
it's going back to user space, then you'd schedule it again.
Yes, that's right. But then it's faulted in, and you need to be really unlucky to have it faulted out again, right? Paged out, sorry. One workaround for this that I thought about but did not implement is if that state is really important to get right 100%, I think we could hook into the page fault handler for the reads. So the scheduler cannot update the state, but it can tag the process to say, well, the state for that page is actually currently wrong. So on the next page fault for reads, to try to access and read the state, the right information will be populated before the process is allowed to read the page.
So basically, so when the other CPU says read this page, it's going to actually take the fault and it's going to actually update the status. So we
That
could
could
actually,
work.
and you just have the status since like the task struct, stuff like that. Say, or just check, are you on the run queue? And then, so when it faults in, say, okay, do it that way. I mean, that could, I guess that work. Good.
All right.
Yeah, we just covered this, the correctness slide by accident.
Overall, I'm curious, what's the the performance benefits versus like avoiding the context switches versus like when you're spinning in the kernel, spin on owner, you have like really specific like MCS locks. So there's a trade-off there. Like, have you determined like which one is better in some cases, which one is better off, even with the context switch still using better cache lines?
I have not worked on any benchmark on this. I mean, I've seen the LWN article about what you were trying to achieve, and I was like, RSec can do that. So I did that path. So the benchmark part and trying to figure out where it makes sense and everything, I leave that to Andre. So,
Yeah, yeah, but I didn't mark already. They were trying to figure out the proper design.
Yeah, because once you incur in the context switch, the MCS properties, the OSQ lock specifically, really boost performance. That's all.
I mean, that would really be an important information to have, because if you look at right now, the syscall overhead is mostly that is schedule out. It's not that you're going into the kernel. I mean, syscalls 20 years ago have been expensive from the hardware point of view, but it's not longer that horrible.
No, with mitigations on, they are.
Yeah, but come on, we're not optimizing for PTI affected machines. No, we don't. It's stupid, really. But give us information about what does it take to get into what's the real advantage, and does it matter? That's the main question. I mean, obviously, everybody out there who does user space spin locks will tell you, oh, of course it matters because it gains us so much performance. And then if you do real world benchmarks, it turns out to be completely irrelevant. So this is the real question we want to have, because the spinning mechanism itself we have in the kernel.
The LPC people have information about that because their own mutex implementation have some heuristics about how much it needs to spin before going to the kernel. So there's already some mitigations in place to kind of...
Yeah, but they're all wrong.
Yes, well, that's why we want to provide the right information from the scheduler to let them easily do the right thing.
But Matthew, the main problem is that today's implementation, and I was yelling at people 10 years ago and told them implement spinning in the Vutex code. And then compare and contrast, because then you can just go into the kernel without having heuristics. And we all know that heuristics suck. So, but the kernel has all the information ready and can do the right thing without having to have a page fault handler and a whatever handler and magically mapped memory. No, it's all not necessary.
So
there's a trade-off.
Yeah, the first metric we need is the cost of doing the round trip back and forth to the kernel.
Exactly.
Compared to,
The patches I sent out with the extended time scheduler thing that I kind of played with, I just did a test with like a benchmark on just measuring like its own little spin locks, where I would grab a lock, do something and release, grab a lock, and then had some contention on it. And then I switched it to a few texts and said, okay, just let it, if it goes in with the spinning and everything, the performance dropped tremendously. I mean, it was more of a micro benchmark, true, but still.
Because you scheduled out on the content.
No, wait, on contention, no, I didn't schedule out. Well,
yes.
Oh, yeah. So, because actually.
If you go in the kernel with Vutex lock, you schedule out, period.
Okay. So.
Unless the other side released it in the meantime.
maybe slightly irrelevant point, but like whenever talking about overhead, it's always good to be aware of like DVFS impact and like all the power management and like, are you accidentally being running slightly faster when you measure the overhead? Which I don't know, like I've seen enough of these overhead sometimes being wrongly attributed, which might not be the case over here, but like at least when talking with app developers, they try to optimize and like yeah, you are running a little bit slower, that's why, and you need to basically mitigate it differently.
Anything else?
Put in an action item for myself. I will implement the Futex spinner, like adaptive spinning, and then I'll run the same test to make sure that, and test to make sure it's not actually scheduling. So I'll add that.
I mean, that would be a nice improvement for Futexes anyway.
I actually implemented some kind of optimistic spinning Futex before, and I sent out a patch. But the problem is there's no user space application changes, so it didn't get merged. Yeah.
Oh, well, I think one of the problems is also we don't know who the owner is. Don't we have to pass?
All this works only with robust Futexes anyway, because you have to know who the owner is. So you have the TID in the Futex field itself, and it's handed in via the syscall anyway. So it's low overhead from figuring out who the owner is, and then you can do the lookup in the kernel, and it's all there, it's all existing code. So it shouldn't be hard to hack up. And I mean, if people insist on using non-robust Futexes, I can't help them anyway.
1 minute. Anyone else? Last minute thing?
That's all we have.
Okay, thank you.
Frederick?
Frederick. Must be CPU isolation.
Yeah, as usual.
Or do you have a demo or anything?
What?
Did you upload your slides?
No. I uploaded.
Did you send them slides?
No.
Okay, so
Right now?
well, actually, do you log into? Are you connected to the internet?
Yeah.
Okay. Do you have an account? Meet.lpc.com. Let's do it right here, real quick. Because we're going. This is, there's no,
You didn't upload, yes. You didn't.
So go to, save it. Okay, save it. Actually, and you upload it to this. Actually, are you logged in here? Are you logged in? It says log in. So, do you have a login?
I can try this one.
Okay.
I didn't prepare your slides. You asked me not to prepare. You told me, oh, you should. I will do. I will make them. It's not hard. I'll prepare you.
Is he a speaker here, or says he's speaker author? Yes, you're there. Wait, go back. No, it should have been in the edit thing. Oh, no, here it is. Click on it.
Okay, yeah, it's easier when we have two. One I use this as default and the one is the custom.
Ideally, it's PDF. It could do other things if you don't.
It's not a problem. It's not a problem to build here. Okay.
Okay, so actually, can you?
Did you upload?
Can you log in? You go on your laptop and upload it, you just upload it to Indigo. He's not logged into Meet, so.
You want me to re-upload it? Well, we can replace like if it takes time, we can make the next position now.
Yes, let's do that.
We'll switch the order of these two presentations, right?
Yes.
Yeah, we are having technical problems. I'm sorry for the inconvenience, but we will switch the order of the two ISO CPU presentations. They are on the same topic. This presentation.
How do I navigate here? Okay. Hello, everyone. My name is Leonardo, and I'm going to present this improving CPU isolation with per CPU spin locks. I give some performance numbers here. My name is Leonardo. I work at Red Hat, trying to work more on real-time stuff. You can find me with this handle, LeoBraz, in those networks. Well, when we are talking about real time, what we want is to run these time-sensitive tasks without interruption. One of the ways of achieving this is isolating the CPU, so no other things are running there. It helps in a lot of workloads. And one of the things that bother us in CPU isolation is that there are APIs. There are other CPUs scheduling work on the isolated CPUs, which should not be happening a lot, right? I'm focusing here in one use case. It's the per CPU caches. The whole idea is very efficient. The idea is that you have a single resource, a global resource, and you try to use it with multiple CPUs, and it's kind of hard because you have to compete. CPUs are competing for that resource. What we can do is to add these caches, and the whole idea is that you operate in local caches, which is quite efficient, and whenever you need anything else, you just lock the resource, and then it works. I mean, you reduce access to like global locks, and it makes things run faster. The thing is with this strategy is if you need to request things, let's say you are running out of memory, for example, and you need to request this resource memory from the other CPU caches, you need to do an API, meaning that you will stop the CPU for doing whatever it was doing, and you will require its CPU time. And it doesn't. Oh,
I took your presenter, so.
What?
Do you need a presenter right now?
Maybe I'm not being able to go to the next slide.
Okay, shoot. I didn't get to. You noticed.
Yeah.
There. Next slide.
Okay. This is how it mostly works. You have your hot path, which is the thing that you use most. You do the local lock, do the local work, local unlock it, and whenever eventually you need to access the caches from the remote CPUs, you will schedule work on that CPU. Could you please go through? Oh, yeah, not mine.
Not supposed to happen.
I'm not ready.
Okay, let's take the presenter and put it back to you. Okay,
This-
so they changed the way things work.
This is a case of CPU isolation that wasn't respected.
What was the name of your presentation?
It's presentation.
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 Oh, presentation. Okay.
Could you do the next slide, please?
I'm just going to make you presenter again.
Okay.
Do you have it now?
Let me.
Perfect.
There's 2 LPC speakers. That's 3 LPC speakers. I don't know which one is us.
And for some reason, I can't go to the next.
Okay. Can you just take presenter from there? There's a little button. Because there's 3 LPC speakers.
Steve.
Oh, okay. Take presenter. Okay, great. No problem. The idea is that in this strategy, this local cache strategy, this thing here generates an API, and that's bad for CPU isolation. So what would be great if we could come with another efficient strategy that doesn't require the scheduled work on isolated CPUs. And the simplest and maybe dumbest way of doing that is using per CPU spin locks. The whole idea is that differently in a different way, unless instead of using the local lock, you get the spin lock, and everything works the same. Whenever you need to do remote work on remote caches, on remote CPU's cache, you instead of scheduling work there, you just get the spin lock, the per CPU spin lock of that CPU, and do the work. And it's great because since this remote operations happen quite rarely, we can just don't worry about the contention. And that Mel Gorman did some work related to that in this commit that I pointed here. It's easier to show this that way. The whole idea is that you replace the spin locks, the local locks with spin locks, and then you, for each CPU, instead of like scheduling work, you just grab that CPU's spin lock. But whenever I say use a spin lock instead of a local lock, what everyone will ask is, well, but spin locks are costly. We don't use them for a reason. And most of those costs come from contention, getting cache line exclusiveness, and memory barriers. Contention, as I explained before, is not a problem because these remote operations are quite rare. I run for hours and I could not get one case where someone tried to get the spin lock and was not able. Getting cache line exclusiveness is not very costly because you are like 99.999% of the time you are operating in your own cache line. You don't need to invalidate cache lines because you are mostly working on your cache line. And the last thing is memory barriers, which are not supposed to be that much expensive, but we are seeing this cost here. Those are for getting numbers here on how much a spin lock, local per CPU spin lock actually costs. I did these 2 tests. The idea is that I run 1 million times and get how many clock cycles that does it take. I run on x86 and ARM, get the number of cycles, and that's it. That's the test number 1, as I said. This test lock here is getting replaced. The reference is local lock, so every number will be like any more cycles. I do use the spin lock, inlined spin lock, and this textbook spin lock, which uses exchange instead of compare exchange, just to be sure to fetch the idea of how much we are expending more needing to do a full CAS operation instead of a blind CAS. The test 1 results is that a normal spin lock on x86 took 35 clock cycles extra, but when you go to inlined spin locks, it goes down more than half. And this textbook example of spin lock takes a little less cycles in general terms. You have this K-malloc test, the same idea, but I created a C group with memory limitations and just did a lot of K-malloc. The locks here were changed in the memcg code. So the idea is that I'm testing on a real example here. And this is how much extra it costs for HK-malloc. On x86, it costs us 9 extra clock cycles. But if you inline this spin lock, it takes like 4 extra cycles for a full K-malloc. On ARM, it costs a little more, but anyway, the textbook example of spin lock here, it became very expensive. That may be the reason why we had opted up for compare exchange. Just a few numbers. Just commenting on like inlining the spin locks is a good way of saving time. I mean, inlining it's enough for getting more than half of the cost of the spin lock. In this example here, it takes even more, like a lot. So maybe spin locks, local spin locks are not that costly, and we can like afford to replace the local locks in this case. The whole idea, I already concluded, but there is a question. Why? Well, preempt-RT already turns local locks into spin locks, which is good because means that someone already is have a success case on that. But there is a solution that we can just afford to, because on preempt-RT enabled, it costs mostly nothing. And there is this question, can we just improve CPU isolation on this scenario where preempt RT needs to be enabled for this improvement to happen? And if that's the case, why haven't we done that before? I mean, we have in preemptive RT enable, we have always to pick a spin lock. Why are we scheduling work on that CPU and not just like grabbing the spin lock instead? And here I propose, I sent this patch before, I propose that the name is bogus. I just could not think on a good name for that. But the whole idea is that you can get, if you can get the other CPU's local lock, in this case of a spin lock, we can create new functions. And instead of like scheduling work on, we can use this helpers, local schedule work on, and instead of like really scheduling, we just grab the spin lock and do the work. The idea of implementing this is basically that you have your function that will not be run remotely. You use just the local lock. And if the test can be run remotely, meaning remotely, not in the same CPU, you can just put the CPU number here. It will do the work and just get out. The idea is that this local lock and here will grab the local lock of the other CPU, which in this case would be a spin lock. And when you will require some remote work, you use this local queue work on, which here I explained that when preempt RT is enabled, it just grabs the remote spin lock, which is the local lock, and do the required work. And that's it. I suppose you can have any questions.
Just real quick, you said convert local locks into spin locks. You mean convert spin locks into local locks?
Yes, the idea is convert local locks.
Yeah, because some
sorry,
of your
I'm
slides
kind of
kept saying converting local locks into spin locks. I'm like, I think you meant the other way around. Just want to clarify that.
Yeah, the idea is to convert local locks into spin locks. That's correct.
Okay,
The local locks came from RT, and they mostly come from the reason that we try to replace the preempt disable sections. That's why they became preempt disable non-RT. We used to have the local end thingy, but to keep the code the same for RT and non-RT, we got rid of it and had the schedule work thing just to have the same convention on non-RT. And yeah, that's mostly it.
What was the overhead?
Come again?
Did you test overhead of the So repeat for that, the overhead.
The overhead?
Overhead of like RT, this implementation in RT, do they have overhead?
What overhead?
Yeah. Okay. Yeah, the implementation of when you did like what RT does with like how you did all this, and I guess you kind of said it too, there was really no measurable was there overhead? So basically if you implemented this without all of RT, did the kernel notice it?
There's mostly no overhead because those logs mostly are never hit.
Right.
The origin use case is preempt disable. And most of the folks that care about it run it with preempt server, with preempt disable is completely gone. So
but I guess it'd be, have you done more benchmarks on this to see how this impacts like normal workloads or various workloads?
Yeah, I mean, that's true here is the example of a real workload. I mean, sorry. Yeah, I replaced the local lock with spin locks for.
And you replaced the spin locks with local locks.
Yes, no, local locks for spin locks.
Wait.
Yeah, I'm trying to get rid of the local locks on these.
So they have local locks here, then you're trying to remove them with a spin lock.
Yes,
that's
correct.
So they are doing that.
Yeah.
Okay.
And I replaced the whole strategy here. So I took the idea of scheduling work on and just grab the remote spin lock and do this stuff. And those are the numbers that the overhead that I found. Does that answer?
Doesn't work.
Hi, I'm curious. I think there's the premise here that
every one of these isolated CPUs actually needs to have this cache data that you're trying to protect. So I don't know the code. Can you tell us, did you have a look at the users and see, do the isolated CPUs actually need to maintain this cache data where you're trying to avoid the schedule work?
On a previous suggestion that I had on a previous patch, the solution was that people said just, well, in this memcg thing, it's easier just not to have the cache, but the cache was there for a reason. I mean, it brings more performance because you don't have to keep operating on the local, in the global spin lock, for example, for getting more memory. So yeah, it can be done, but it impacts performance. I'm trying to get with a solution that doesn't, or impacts as little as possible.
Thank you.
Yuri, and then Wayman. We have 2 minutes, yeah.
In the case, you saw that inline spin lock has a pretty good performance benefit, but the fact that the inlining of spin lock code is controlled by some configure variable, and by default, they are off.
Yeah.
So if you want to use it, the reason why they are off is because we don't want to increase the size of the text, and
Yes.
also the function size will get increased if they use spin lock and spin unlock. So do you think that will be useful to have a variant of spin lock that explicitly inline it, so that it can be used in the case of the local lock thing?
Sorry, could you repeat the question?
My question is, do you need a special variant of spin lock and spin unlock that are explicitly inlined to make sure that you can get the benefit without affecting the other spin lock code?
Yeah, what I did was using the raw spin lock. If I recall correctly, that was the raw spin lock. The idea is that it's already inlined. There is, as you said, if you just do the spin lock, it won't be inlined. But I went down in the chain there and replaced the spin lock type for a raw spin lock type. And on both systems, it inlined the spin lock for that code specifically. I mean, I'm not inlining everything in the kernel just for this those 3 implementations that use it.
Okay, yeah, what spin lock is inlined. Yeah.
I think we can take it offline, but I was wondering about the actual, let's say, benchmark that you actually run when because you said remote operations are not that frequent, but like we have particular situation where we actually see lots of them. So I was just wondering if you can provide more information about the actual workload that you run.
The workload that I run?
Yeah, to actually be able to say, I don't see many of the remote operations.
So this is time.
Yeah, we can take it offline.
Sure.
We have a chat online. Please log in and actually answer. Like, you actually can talk
Sure,
in chat.
I'll do that.
You guys work for the same company.
Yeah,
we can chat.
That is why I said we can. Yeah.
Thank you, everyone.
Here you go. It's not me, it's there. Yeah.
It's okay?
Yeah.
Okay, hi everyone. So this is my yearly CPU isolation talk. I do that for several years now. So this is going to be about all the stuff that have been done since last LPC on the CPU isolation front. Quick reminder what CPU isolation is. So briefly, you have a task that you want to execute on the CPU, and you don't want that task to be disturbed by the kernel. So from the lowest level to the highest, you don't want to be disturbed by IRQs, exceptions like faults, and then tasks and work queues and stuff like that. So this is a very extreme kind of workload. And this is typically configured using the no-hertz full kernel parameter, right? So you just pass a set of CPUs that are going to be isolated forever until the last reboot. So since last LPC,
So for several years, one of the biggest issues that we had was the VMstat work queues. So VMstat, I guess most of you know what this is about. This is statistics gathering from memory that you can access through sysfs. But the VMstat thing I'm talking about here is the work queue component that folds the memory statistics per CPU. And this is a work queue that executes every second. And it's very annoying for extreme workloads that don't want to be disturbed, because that's every second, one interruption, and potentially scheduling a work queue. So very disturbing. And there have been several attempts across the years to solve that solution, from Marcello Tosatti, led by me through solutions that didn't work. We first tried to do explicit quiescing of that VMstat thing through explicit calls, like through PRCTL. So the goal was that before running extreme workload, you issue a PRCTL that folds all the VMstat statistics. So then you don't get to suffer from the VMstat timer and work queue. That didn't work because of many reasons. We also tried implicit quiescing, which involved folding the VMstat statistics on every return to user space. But here the reason was obvious. It was quite some overhead on every syscall, every interrupt. So that didn't work very well. And eventually they realized with the memory management people that we can live with some imprecision, inaccuracy of VMstat statistics. So we don't actually need to periodically fold all the statistics. We can just live with a few calls from time to time, folding the statistics. So on the Hertzful CPUs, we just don't schedule any more VMstats. That's solved. Actually, maybe officially solved, and maybe unofficially it's a problem, because we have seen lately some issues with memory pressure artificially created by VMstats. And maybe Thomas is going to talk about that.
No, I was just having a question. Why don't you do it remotely? I mean, we had it in RT for a while. Have locks around it, which are usually not contended because they are per CPU. And in the case of isolating them, then you just fold it remotely. And because then the isolated CPU is not going to contend on the lock. And so you just have to touch the foreign cache lines, but you can delegate it to the housekeeping CPU. That would be the obvious solution for the problem.
Well,
without all the heuristics.
I think they considered it, but they just thought that simply not actually folding the statistics that often was fine, but it seems that there is a problem. Yeah, so maybe, I don't know.
Not surprised.
Yeah, right. Some memory management people in the room wanting to solve that one day.
So you have to take presenter again?
No, I need stuff.
Oh, you did?
Can you go back and forth?
It just worked. Oh yes, you're not you. It is the. No, it's not his username.
Oh yeah, okay. All right. A brief word about deferred IPIs. So IPIs, of course, are some source of disturbance for CPU isolation. One solution for some IPIs, mainly those that don't have callbacks to carry on, one solution is to defer IPI execution when CPU runs isolated until that CPU comes back to the kernel. So as long as the CPU is running in user space, it can defer the execution of an IPI until it goes back to the kernel. So Valentin is working on that. I guess.
What kind of IP are we talking about?
Can I use that one? You can use this one, yeah. It just, you won't be on camera. It's use that other one. So the camera follows that one.
So the latest status was we were looking at text update for static keys, and we sort of got consensus that we could defer some IPs for VM allocs. The problem I'm facing at the moment, well, is mostly time to work on that because I've been preempted by other stuff. It's mostly the infrastructure side of things because I've been working on having tooling to make sure that deferring those IPRs is not going to cause issues. For static keys, for instance, we don't want static keys in early entry code that can be changed at runtime. So we have this little annotation for read-only after init. So those static keys are okay. If they only modify that init, then we're good. We know they're not going to be modified. So if we anchor to them in early entry code, they're safe. I've realized that we have some that don't match that. And it's more of an infrastructure issue. So for instance, because of all of the nice mitigations we now have on return to user space and entry to idle, one of them, for instance, is just as we are about to enter idle, we have a static key that we can hit. And I've been using the no instrumentation annotation as this is early entry. Unfortunately, in this case, this is more like early exit, which doesn't matter for us, but my instrumentation is picking this as like a problematic log. So I need to spend time, unfortunately, on the infrastructure that checks that this is all same. That's where I'm at the moment.
Okay.
Anyone else? You're the rugby player. Yep. Anyone else? Or continue?
Okay. CPU set v2 has seen some improvements. Well, enhancement. So CPU sets is used for CPU isolation in order to isolate a given set of a task to some partition of CPUs. So if you want to run a critical task to say CPU 2, you create a partition of CPU 2 and make sure that is not going to run anywhere else and it's not going to be disturbed by other tasks. On CPU set v2, in order to have an exclusive set of CPUs, you have to create a kind of partition that is called root partition, which is not to be confused by the top-level root partition. It's actually a type of partition, right? And if you want to create a root kind of partition, the constraint is to have the parent partition to be root as well. So, for example, here we have the top root C group, which has 8 CPUs, 0 from 7. We create a CPU set 1, first child, which contains half of the CPUs, and it has 2 more children, one of which has 0 and 1 CPUs, and the other one has 2 and 3. If you want to, for CPU set 2 and CPU set 3 to be exclusive, like if you want to be sure that CPU set 2 has CPUs 0 and 1 and no other CPU set is going to have 0 and 1, you need to have those CPU sets to be root. And if you want CPU set 2 and CPU set 3 to be root, the constraint so far was that CPU set 1 had to be root as well. But on some workloads, you can have a tree that is much more distributed. And so it's, I don't know exactly why, but it's apparently complicated to have all these distributed tree to be root, made of only root partitions. So there is a new feature here that has been introduced, which is called the remote partitions, and which doesn't suffer from that constraint to have a parent root partition, which means you can have all your ancestors except the top level as non-root partitions. So for example, here, if you want to have CPU set 5 and CPU set 6 to be root partitions, you don't need to have CPU set 4 as a root partition. But you have to make sure that all the ancestors of CPU set 5 and CPU set 6 to define a set of exclusive CPUs. Do you understand what I'm saying? Yeah, kind of. It's very complicated. Yeah, it took me some time to understand the thing, to be honest. So, once you have written the CPU's exclusive file of CPU set 4, and you have written it for CPU set 5 and 6 as well, and you make sure that CPU set 5 and 6 have mutually exclusive set of CPUs, and that CPU set 5 and 6 are subsets of the exclusive CPUs of CPU set 4, then finally you can define 5 and 6 as root partitions. And those are remote root partition. Is it clear?
It never gets clear.
Kind of.
I'm just missing the use case.
Me too. Ask the original author of the.
And that is the version 2.
I only had time to understand how it works, but not as much time to understand why.
The use case is for containerized workload, like the warehouse OpenShift. They need to manage all the sub-container on a high-level CPU set, but then it doesn't want to be using exclusive CPU. So just using within the high-level C group, you can have a set of CPU that contain both exclusive and non-exclusive one. So the control daemon will use the household one, the non-exclusive one, and then distribute the exclusive CPU down to the lower level C group or CPU set to be isolated CPU. That is the use case that are requested by our OpenShift team. So that is the reason why we implement this feature.
Yeah. So real quick, one last thing, or maybe I'll. So I'm kind of lost on this as well.
Me too.
And I'm trying to understand the difference. Wait, so what is the difference between a local and a remote? I don't want to be like, I don't want to be.
So a local has to have all its ancestors as root partitions, whereas a remote root partition has to have all its ancestors as non-root partitions, except for the top level.
Okay, maybe I can explain. The original implementation of CPU set partition is that it get exclusive CPU from its parent. So to get that exclusive CPU, the parent also need to have exclusive CPU. And so you have to be a partition root before you can distribute the exclusive CPU down the line. With the new version 6.7 kernel, we add a new control file called CPU set.exclusive. CPU set.cpu.exclusive. And that allow you to distribute the exclusive CPU down the tree without actually becoming a partition root yourself.
So I'm just curious if that CPU set 4, the exclusive didn't have to be 4.7, or is that the different? Like right
Usually, the exclusive should be a subset of the CPU set CPU. So the CPU set CPU contains both the exclusive CPU and the non-exclusive one that can be used by the local C group. So the rest get distributed down the tree.
Okay. Anyone else? More?
Yeah, some more. How much time?
I still have like 5 minutes.
Okay. So other details that you can check afterward on the record. And finally, the no hertz full CPU set interface that I'm talking about for 10 years. So what this is all about, no hertz full has to be defined on boot using a kernel boot parameter. And once you do that, it's fixed on stone until the last reboot. You cannot change that on runtime. And for 10 years, the plan was to have a CPU set interface so that you can change that on runtime. But after working on that for several years, I realized that it's very complicated to do. It's not unfeasible, but it's going to bring a lot of complications on the kernel. Mainly when you change, when you add no hertz full dynamically, you have to protect against concurrent source of disturbance queue. And for that, you need to protect using RCU read-side critical sections or per CPU, using a per CPU dedicated read-write semaphore on several places, such as case thread creation, because there is an affinity setting here, and you want to make sure you don't mess up concurrently. VM stats, K-thread affinity setting, many things that you need to protect against. Yeah.
Did you think about just making it in a way that you have to soft offline all CPUs except the boot CPU and then configure it and bring it back up, because that avoids all that mess? Because it tears down all the threads, all the affinity settings are gone, and you're starting basically from boot, right?
Yeah.
So that would be way easier than
Like
trying
using
to
machine?
adjust it on the fly, because that's going to be another mess.
Yeah. Like using stop machine or something
No,
like that?
not stop machine. You just do you offline all the CPUs. I mean, if you configure reconfigure that thing, it's not going to be that you run the full workload already and then you magically reconfigure the whole machine. I mean, you can do that, but does it make sense? I don't think it makes sense.
Look at the MMIO tracer when you enable it, because the person who enabled or wrote the MMIO tracer didn't want to work with SMP. So whenever you enable the MMIO tracer, it shuts down every CPU but one to execute the code. It also finds a ton of bugs in hot plug.
I think it's even on the documentation for you to remove the timers. It advises you to turn the CPU off and on.
Really?
Yeah,
But-
it's a pretty, it's documentation. It's pretty old.
Yeah. Yeah, I don't know. I need to check in detail because, yeah, okay. Need to check that. Yeah, right. Yeah.
If you want to isolate, you want to remove everything anyway.
Yeah, that makes sense. I need to check that.
Yeah, this is not a
That
performance
solves-
critical
that should
operation,
solve
right?
big part of the problem.
And the person that would say that this is a duct tape was the person telling you to.
Yeah, and also if you want to isolate, you probably want to rebuild all your SCID domain in the scheduler, because they will going
Yeah,
out.
yeah, that's
so,
too.
and that's an easy way also.
Yeah, right.
Yes, I'm not sure if there might be workloads that are already, let's say, using a subset of CPUs that don't want to be affected by a reconfiguration or
Yeah, but then you can just offline
Come
the
on.
CPUs you care about, right?
I mean, either you do offline only DAM, or you actually, I mean, it's mostly, you won't reconfigure a machine which is already running the big database and whatever the hell. I mean, that doesn't make sense. That's an artificial use case and a mostly academic problem to solve. Yeah. I mean, there's a lot of academics in the room.
It's one thing. It's easier than rebooting.
Yeah, of course.
It's easier than rebooting.
Yeah,
but rebooting is easy actually.
No, I mean for the people. At
Yeah,
least
yeah,
the
right.
system is up.
Your boss wants to speak.
Yeah.
Talking about something like a Kubernetes workload. That's not something you want to, I mean, if it's really in progress and running and you want to do some reconfiguration, you really don't want to try and tear the whole thing down, right? I mean, so you're going to have if you're going to go in and say offline all the CPUs, yeah.
No, I mean, is it about particular CPU set reconfiguration or about bringing the whole thing into no-heads full in the first place?
Yeah.
I mean, that's the main question. What do you want to do?
Well, doing the offline is still going to be faster than rebooting because because when you have a power on self test that takes 10 minutes, you really don't want to reboot, right?
By the way,
So,
you're entering the next phase. I don't know if you want to interrupt it, but it's yours.
There you go.
And maybe one thing that makes it easier just to turn the CPU off, you might not need to turn them all off back and forth because of that string that we have on RCU. Just have a per CPU value and turn that on and off, and then go to the next, on and off. You don't need to do all back and forth, maybe. Maybe turn makes things easier. I don't know.
Yeah, I'm going to get, yeah.
Because it takes all the stuff
Mm-hmm.
and rebuilds it when we online.
Right.
It's like rebooting.
But it's like reboot, so
it's more free.
it's more free. Yeah.
It's just one step.
Because the complication is not just that, it's also on RCU. Just put the slide on here. So the offloading and de-offloading callbacks. Even if you put all CPUs down except the boot CPUs, you still have to work with. Actually, it could simplify that as well, maybe.
Exactly.
Yeah, you get it.
Job security.
Yeah, it's worth considering.
Yeah, we need to move it.
Okay. Thank you.
Thank you. Sure.
It's yours.
It's mine.
Yeah.
Do you have slides?
Sure.
Yeah, finally. And that's an improvement from the last
He pestered me so long about not having slides for that Q&A. I made slides.
What is
including the most important things like roadmaps and whatever, you know.
You were the boss.
Okay, state of the audience. How is this working? Oh, here we are. So Preemptor is ongoing for almost 20 years now. So it becomes 20 years only anniversary next year in September. For me personally, it's going to be 25. I started working on Linux real-time in 1999, so it's going to be a big party then. Are we done yet? Kind of. Because there's this thing, PrintK. Come on, people. Pardon? So what can be so hard about printing a few characters on a console? Incredible. Yeah, it has to work from everywhere, including NMI in the worst case. So we have to do it from any random context, which means we have slight concurrency problems. We have magic driver locking problems. And what we want to do is to have synchronous and asynchronous output. Right now, PrintK is fully synchronous, mostly. There's some way to not print synchronously. That's in situations where we actually can't, like in the middle of scheduling. We can defer it, but that's an awkward mechanism. But everything else is pretty much synchronous, which is stupid to begin with. Because if you boot up, I mean, look at the messages. It's the hell of noise. Why would you wait for all of this non-information while it goes up? It doesn't make sense. So what we want, and coming from the RT perspective, we put console output into threads for a long time, but it's not a real, the hacks we had in RT were not a real solution, and we wanted to make it useful for the mainline, for the non-RT part of the kernel too. And a lot of people are waiting for threaded consoles, and we're finally zooming in. So yeah, it's something we started to work on in 2018. And we have something like 300 patches. I think it's 400 by now. This 6.6, the 6.7 merge window got another 100, I think. It's mostly preparatory things, but also now we got the core handover mechanism, which is completely lockless. Yeah, it's kind of lockless. It's stateful. So that this handover mechanism is the core thing to go threaded, because then we have a way to actually say, okay, we take over either in a collaborative way when we have something running here doing console output like the thread, and we have an emergency message on the other CPU. We can ask nicely, hand it over to me. Or if the emergency happens on top of something which runs on the same CPU, then there's no choice than to take over host down. But as we have state, we know that there is something fiddling with the console, and we can act accordingly. Right now, the original console implementation is all about, let's print and see what happens. So hope-based, basically. There's also no way to say, okay, do I have a safe console to print in arbitrary contexts, or should I avoid printing it when I just crashed in an NMI? Best example is graphic drivers. So if you have to do kernel mode setting from NMI context, it's almost guaranteed that you will die. So, but that, because everything is synchronous, we write out to all consoles on the first line we print, which means if you're lucky, then you get the first line of the dump on the serial, and then it goes south because it explodes in kernel mode setting. So these are the problems we are trying to solve. We're getting there. There are 3 final patch sets series out there. Some of them are in review already. So we're closing, and don't ask me when it's done. I'm refusing to give answers when it's in terms of print K. Print K totally fails my predictions. It's unpredictable. And I lost my crystal ball, so no, I'm not going to answer that question. I was talking about this a couple of days ago to somebody, and truly, the most of the estimations we had in terms of bringing stuff from the RT tree upstream with all the involved effort, like cleaning up CPU hot block was something like 800 patches or something. The estimation was 1.5 years roughly. It took us 19 or 20 months, so it wasn't that far off. But print K really fails me. You can estimate what you want, it's going to be wrong. So that's where we are. Hopefully it's coming soon to the mainline. I'm positive that it will happen before the 20th anniversary. So we should see it sometimes in the near future. And with that, I'm up to questions.
Don't be shy.
We get a pony with it.
A pony?
When you merge, we get a pony with it.
Yeah, sure, sure.
All on.
You sent the pony patch, right?
Right, I'll send you that.
Moving on from ponies, what are some of the changes that happened since last year in print K, and how does that? Oh, I don't know what kind of words I'm looking for.
Pardon?
What are some of the changes that have happened in print K since last year in your batch set?
So what are the main changes for print K right now?
Since last year, yes.
Since last year, I think conceptually, from the concept itself, nothing fundamentally changed. John? Yeah, John knows better than I.
So a year ago at LPC, we presented a proof of concept with this whole new threaded and handover idea. And this idea has been preserved for the things that are going in the main line, but we've reduced some of it because the problem is there's about 76 console drivers, and they need to be made compatible with this new stuff. And so we kind of got the idea that it might take a while before all 76 drivers are ready. And so one of the big changes that me and Peter Mladic, the print K maintainer, have been working on is just trying to change this model so that the old model will continue to exist friendly with the new model. So we can, one at a time, change over these drivers, but the drivers that haven't been changed over will continue to work exactly like they've worked now. And so that was actually quite a lot of work over the last year. How can we try to not marry the two, but get them to work together so that, you know, because if you have some drivers that are using the old stuff and some drivers that are using the new stuff, you know, you're using graphic and you have a 8250 serial, one of them's using the old method and one's using the new method, and we still want the system to function well. And so that was actually a lot of the things we've achieved over the last year.
Yeah.
Why are there so many console drivers, like 76?
You start from serial.
Yeah,
and then
they're
counting.
mostly serial. There really is. There's really only one graphic one, and like 75 serial, and then there's USB serial, but I don't know if that counts, but that's a disaster for itself. But
And virtual consoles, obviously.
So after let's say that they're done that work, all the print K, let's say the message is becoming that they're asynchronous, or some specific let's say message can be synchronous.
So the idea is that we, for all the default noise, we just do asynchronous and have a thread per console. Because right now, if your terminal console is way faster than your serial, but you have, right, in a synchronous model, you have to wait. So everything is slowed down to the slowest console possible. And for regular print K, you just delegate it to the threads and they eventually catch up. In an emergency case where you really want to get it out, you switch to synchronous. So it's not fully synchronous, not necessarily fully synchronous. There's some details to be sorted out, because right now what we aim for is that we at least dump the most important part of the message first into the message buffer before we try to output. Because if you die during output and you die already on the second line, you lost everything. Even a crash kernel can't recover the information. So the idea is to say, okay, let's dump at least the important part, not the 50,000 lines of ftrace dump or whatever, but the important parts first into the message buffer, and then depending on the availability of safe atomic writing consoles, pick them first. So one thing Linus was asking for, if you have persistent memory as an option, then you obviously want to write the persistent memory first, and then go to serial or go to graphics. Because if you die in the graphics driver during output, it doesn't matter. You have it persisted already. So that's the thought behind it. Okay. Getting away from, oh, it might work. Print and pray.
Just an add-on that if you really want to make sure that everything is flush, that there is a new function for flushing messages, which is used, for example, during suspend or in panic and so on.
Yeah.
So,
Hey, Thomas.
Hi.
So let's imagine print K is done, gets merged in. Are all architectures going to be on the same level? And what are the challenges after the merge point?
So if print K is there, we basically can assume that we have at least the 8250 driver in there. We can enable it on x86 and ARM64. The amount of effort to enable RT on at least a half-phase recent architecture is very close to zero. Sebastian, there was a RISC-V enablement patches. It was pretty small, right? So it's not. So it's not much of an effort anymore to enable it because we brought all the interesting parts into the generic code. So there might be some details left in the architectures to tackle.
So RISC-V works, there was not a lot to do. They have perf working, they have interrupts, they have generic infrastructure for entry exit. So they have everything out of the box, so this works well. PowerPC 64 on the other box is a different issue because they have special MMU handling and so on.
Right.
So this is busted. I was trying to fix it over the years, but at the end I was like, okay, maybe for later. And ARM64 isn't much as well. There's still bits that are missing.
There's two small patches or out of 3 right now.
Right, so ARM64 isn't much. i9-15 is disabled. This is a big mess for upstream.
Right.
So this needs to be discussed, for instance. Right.
Yeah, so i9-15 is a horror show, but i9-15 is a horror show without RT already, so that's not, and there's some solution on the way. People are actually writing a brand new driver covering at least the last decade of Intel graphics, because i9-15 is, from a design perspective, the driver is so broken, it's unfixable.
Yes.
I mean, you would end up rewriting it completely, so they started from scratch.
You're looking forward to a question from me. I know.
Sure.
I want to ask about roadmaps. So the question is, once print K comes in, do you think you can piggyback preempt RT in that same merge window, or are you going to definitely split it?
No, I can't. So if we have it already in next print K, I'm just going to piggyback, or at least try. I mean, there's no big argument because it's. I mean, it's we have all the stuff in there. So if you do not enable it, it's not going to change anything because all the if-def is already there. All the compile time conditionals are already there. And if you enable it, you ran preempt RT before, so what? So I don't think it's a risk.
Circling back to i9-15, is there any RT enablement for the new I don't know how to pronounce it, XE driver that's coming up for Intel, 12th gen and later?
I think the driver itself should be just as simple and RT safe as any other graphics driver. It's just i9-15, which simply doesn't work because i9-15 people decided to have creative locking for the wrong reasons.
So i9-15 has a lot of quirks, and I've seen patches over years, and they never responded. They never got merged. I had bug reports for the AMD GPU drive, for instance, and it was a week, and everything was merged after I sent patches. So it kind of depends on the people working on it. So AMD folks were pretty responsive, so it worked well. And i9-15,
yeah, but it was pretty minimal invasive on AMD. It wasn't that horrible as on the i9-15. Right?
Well, it adds up. you start with 2 patches and then 5 releases, then you have 10, and then we have
Yeah,
15.
yeah, sure. But it was, from a design perspective, it wasn't that horrible as i9-15.
Maybe.
Because if you want to fix i9-15 properly, you end up not with 10, you end up with 100 or 1,000 or 100,000. I don't know. So, fun. Yeah, and it might work by some definition of work. So, any other questions? No. Great.
Good.
Lunchtime.
Lunchtime.
Lunch.
That's why you have so many household drivers. Because i9-15 doesn't work. To the bug.
We modified the, it used to be like 10 meters. Now we say to give to let people know, don't touch that. Because that's exactly what it does. It kicks everyone off.
É que assim, meu sentimento, mas a galera pegou uma questão. A pergunta é assim,
Like wrong button. Hey, you know where he said there was some samples?
I didn't want to do it.
Everything seems okay. I don't know.